Okay, so I guess we can start, right, Enrico?
I guess I believe so.
Okay. Okay, so welcome everyone to the third day of our conference. Today we will be talking about the connections between infrared and ultraviolet physics in gravity, about quantum gravity and some other related stuff. Just before starting, let me remind you that at the end of every talk, there will be some time for questions. Please use the button to raise your hand in Zoom, and we will see how much time we have for questions after the talk. And if you have any other extra question or there was no time to answer everything, you can wait either to the discussion session after the break or use the Slack server where we can have a more slow discussion and more deep discussion on some of the topics. And with that, I would like to introduce our first speaker today, which is Lasma Alberte from Imperial College in London. Lasma has worked in a lot of things, in massive gravity, holography, and more recently in effective field theory applications to the connections between infrared and ultraviolet physics. And she will be talking today on positivity bounds in the presence of gravity. So thank you very much for coming, and Lasma, the floor is yours.
Yeah, hi everyone. Thank you, Maria, for the introduction, and the organizers for organizing, and all the speakers of previous days and the days to come. Yeah, so I will be talking about positivity bounds in the presence of gravity. And although I will give a review on like basics of positivity bounds and also some outlook based on other people's work, the main content will be based on the two papers of last year, together with my collaborators, Claudia Deram, Summer, Jadley, and Andrew Tolley, all of whom are in the audience, which is very intimidating. So you can also ask questions to all of us later then. I'm very sorry, I don't know how to switch the slides. Oh, yes, now. So let me start with a nice reminder to everyone, ourselves. Let's say that that the general relativity should be considered as an effective field theory, and you can modify it if you take Einstein's GR as the starting point. You can modify it in various ways. You can do IR modifications, and you can add higher derivative corrections like curvature squared operators to the theory. And those higher derivative corrections usually come from some UV completion of the theory, which we unfortunately don't know for sure what it is, string theory being a very compelling candidate. And the question that we would like to ask is what modifications of Einstein's theory are theoretically viable, which of them make sense, and which of them can come from some hypothetical UV completion. Because otherwise, if we start just with like an EFT for gravity, which is like Einstein's theory, and those higher derivative operators, it's like a bottom-up approach, and we don't really know whether it would make sense at high energies, like even higher energies, or they would actually be in the swampland of the string theory. The other danger is actually if we go from top-down approach from the string theory, we risk of being like standing under the lamppost of string theory, as people say that. So it would be nice to ask whether there are like bounds, theoretical bounds, like consistency bounds on the theory criteria, which we could use to distinguish between possible modifications. I have here some very schematic energy scale shown here, where like the highest of the energies that arises here is the M Planck, which is really the utmost scale at which we know that Einstein's theory breaks down. There are some intermediate scales, like M for me very often will be a cutoff scale, which could be the string scale, which is the scale at which the higher derivative operators come in. And so it could be, yeah, either the string scale or like just the lowest mass of the next particle in the theory. And I have also put here the lambda 3 scale, which is another strong coupling scale. If you would be modifying the general relativity in the IR, then you would have to give up the M-Planck scale as being your high energy cutoff. You would have to work with a much lower cutoff, and you would need some sort of UV completion earlier. Like IR modifications, they are nicer in a way that we can actually test them much better. Like this picture down here is like the 100 years ago of the light bending experiment and confirming the Einstein's theory, and we still have to the theories have to be compatible with Einstein theory at low energies. And there were many talks yesterday, several about the Einstein screening mechanism, how to make those theories to recover a GR at the solar system scales, for example. And here, of course, yeah, there's the swampland picture as the opposite, because just to demonstrate that we don't really have that many experiments saying us something about the high energies. Like even gravitational waves, the scales they measure at first glance are closer to those lambda 3 scales than the M-Planck and higher scales. So yeah, and having shown this, I wanted to say that what is nice about the positivity bounds that I will be talking about today is that they actually don't care whether it's hard or easy for us to test the physics. They can be used, they are very democratic. You can check the IR modifications, you can see whether they make sense from the EFT point, and you can also look at the higher derivative operators. So let me start with the positivity bounds in the presence of gravity. So positivity bounds, I'll give a very short review. So what are they? It's like when you assume the existence of Lorentz invariant UV completion of your low energy effective field theory. If you assume that such a UV completion should exist and that it should be unitary, local, crossing symmetric, this imposes, this manifests itself like in the optical theorem that you can, that has to be obeyed, and locality manifests in like analytic properties of the scattering amplitudes. And these conditions lead to constraints on the signs of the Wilson coefficients in the low energy action that are the so-called positivity bounds that we are after in this talk. And they are usually positivity bounds. What you work with is the 2-to-2 scattering amplitude in any of the low energy theories that you consider. And when it's written in terms of the Mandelstam variables ST and U, the amplitude has actually a very simple analytic structure. If you have 4 identical particles of mass m, and you have 2-to-2 scattering between them, then the amplitude has physical poles at the center of mass being equal m squared, and the same with the in the U channel. And there are 2 branch cuts which start here in the complex S plane. They start from -infinity to 0, and then from 4m squared till infinity, and they are analytic. The amplitude is analytic anywhere else, and this allows you to write the amplitude in terms of the Cauchy integral, where you just take this small green region where it's analytic, and you write it in terms of this integral. And the main juice of the positivity comes when you deform the contour integral into this bigger one, and then you just look that there are 3 kind of contributions to this dispersion relation. The first one is just coming from the poles. These are the residues of the poles. Then there are contributions from the discontinuities which are expressed here as the integrals. And then there would be contributions from this high energy arcs, which we just approximate by two terms, which is like constant in S and linear in S. So the positivity of this amplitude, it comes from when we look at the discontinuities. We can relate the discontinuities with the imaginary part of the amplitude, and the imaginary part instead can be related to the total scattering cross-section via the optical theorem, which is positive. And we can, to derive the simplest form of the positivity bounds, we just can subtract the poles and impose the positivity on the second derivative of this pole subtracted amplitude. And this really just comes from this dispersion relation, and it's the simplest way how to impose the positivity bounds. There are many more positivity bounds, like on higher derivatives. They can be either in the forward limit, which is how they started, or they can be at finite t. What is important more is also the Frouissard bound. It is important, especially in the context of gravity, because to derive the positivity bounds, we do need to assume something about those contributions at the infinity, because on those arcs, they are not finite. The integral of the amplitude with respect to divided by S is not finite. So we have to assume that at high energies, the hypothetical amplitude that we don't know the theory, but we do assume it about the amplitude, that it decays slower, that it doesn't grow with S larger than the S squared, so that this limit goes 0. And this assumption allows us to write this dispersion relation with two subtractions. And strictly speaking, this is the Frouissard bound is only valid for massive theories with a mass cap, but we do expect such behavior also for gravity, although it's massless, because we have some indications from the Regge behavior of string amplitudes, and this really is a crucial assumption, because without assuming this boundedness, we would not be able to work with the positivity bounds at this order. We would only be able to constrain like higher order coefficients. So I will also touch on, I will talk about the improved positivity bounds, which are sometimes not talked so often about. And they are mostly important when you look at one loop amplitudes, including one loop processes. And this can be stated when you look at the optical theorem as it's written in this form, where you write the imaginary part of the amplitude as a sum of the contributions from all the possible intermediate states, where like I for me is the initial and final configuration, which has to be the same because we look at the elastic scattering processes. And this optical theorem expresses it in terms of like all the possible intermediate states, and the positivity comes from the fact that each contribution to this sum is positive on its own. And so to improve the positivity bounds means to move all the known contributions to the left-hand side. Like the more we know, we just remove it to the left-hand side of our positivity bound, meaning that we not only look at the S squared contribution, like the double S derivative on the amplitude, we also take off all the discontinuities that we come from the states running in our loops that we know about. And that will be important when we'll talk about QED, where we know that there is the Euler-Heisenberg theory, which describes like modifications to Einstein-Maxwell theory. But the physical origin of that is actually that we have integrated out the massive electron. So let me talk a little bit about gravity. What happens with the gravity, or what we would expect when we think about positivity bounds in the presence of gravity. And one of the big swampland conjectures, or like our guiding principles on how we look at the UV corrections to GR, is the weak gravity conjecture. And this is known as the bound on the charge to mass ratio for any charge states of mass m and charge E in the presence of gravitational force. It can also be, called like the gravity is the weakest force, and like the weakest version of the weak gravity conjecture is when we think about the black holes in gravity, and we ask that the extremal black holes are themselves those charge states that have to obey the weak gravity bound. And the extremality condition is saturated in Einstein theory, but whenever you have like higher operators correcting the Einstein theory at high energies, then it also changes the extremality condition on the black hole. And the weak gravity conjecture, if we use it as a fundamental tool, it would tell us what those higher derivative corrections, what they would what is the sign, what should be their sign. Like, in this case, the higher derivative corrections are parameterized by the two couplings, alpha 1 and alpha 3. I will come back to them later, but here it's just like saying that this condition can tell you something about the quantity or the signs of those coefficients in your effective action. And there have been claims that the positivity bounds actually give you this result, that like that positivity bounds would impose this condition, and in that sense it would like prove the weak gravity conjecture. I will unfortunately argue that it's a little bit premature to make such conclusions, and I hope it will be clear to everyone why is that so. The problems with positivity bounds in gravity is the infamous T-channel pole, and the T-channel pole is present in every EFT where there are matter fields minimally coupled to gravity, because the scattering amplitude, like between 2 to 2 scattering between those matter fields, they always involve like 3-level graviton exchange, and this contribution from the massless graviton exchange always comes in the amplitude as s squared over t. And in forward limit, where we like to evaluate our positivity bounds, or even just in the physical region of the amplitude, this always dominates, and it is singular, and even singular in the forward limit. And when it dominates, it doesn't allow us to actually constrain the dimensional constant, which depends on the EFT couplings that we are interested in. So it just like completely obscures the view of what we could fish out of the positivity bounds. And the question is like how to work around that. And there have been claims, suggestions that we could just discard this pole, and the positivity bounds on those couplings I showed on the previous slide for the weak gravity conjecture, they have been derived exactly in this manner by discarding the pole. There are some arguments, like very, very nice arguments that one could do that if we would compactify the gravity down to 3 spatial dimensions, 3 space-time dimensions, but somehow it's still we would still like to show that there's something a little bit faulty with those arguments, because the results you get just don't really match with what we know from our UV theories. So I will start with a very, very simple toy model of 2 scalars, just to show that what happens if you just drop the pole, that you could get like very strange results by just dropping the T-channel pole and imposing the the positivity bounds. And I will look at effective field theory of two light scalars. It's like as simple as it can be. There's the Einstein term. There is one minimally coupled scalar field, which is just a spectator field, meaning that it is scalar here, but it is not necessarily a scalar. It could be just any matter field, which would watch what the other light scalar is doing only through gravity. And then there's like some phi theory for a scalar phi, which is renormalizable effective field theory. And naively, you would think that in this theory, everything is like completely fine until we hit the Planck scale. And so what I want to show is that it's actually not really true. And for that, we will look at the scattering between the spectator field and the phi field, and from this cubic vertex. And I'm focusing on the cubic vertex because, I mean, we checked also the other vertices, but they don't have the necessary S-squared contributions to the scattering amplitude. So they just don't contribute to the positivity bounds. And so the processes that we are looking at in this scattering is just like the three-level graviton exchange between the two fields, phi and chi. Then there is one loop process. Here, please don't pay attention that it's bold. It's still the loop of the phi field coming from the cubic vertex, and also this one is the phi field from the cubic vertex. And we find that just computing what the amplitude is, the second derivative of this amplitude, once we drop the T-channel pole, it comes out negative. So it's like you get a violation of the positivity bounds immediately, just like that, with this very, very simple theory. And we've checked that you could say, yeah, you didn't include all the other possible couplings between the two fields. We checked all the normalizable operators, like the other cubic interactions between two scalars, or the quartic operators, and all of them give only negative contributions to the positivity bound. So there's no way how to make them positive, which is working with some renormalizable theory. What we did find is that you could satisfy those positivity bounds you get from subtracting the T-channel pole if you would add new interactions that are renormalizable, like with this is an example interaction that would work, and because this gives a positive contribution to the scattering amplitude, such that you can satisfy the positivity bounds if this relationship is satisfied between the operators. But what we want to show is that assuming that there's no big hierarchy between the scale at which the cubic interaction happens and the mass of the scalar phi, that this leads to a very low cutoff scale. Like this scale lambda is the scale at which we had to insert this non-renormalizable operator. And you can see that it comes out like it's the physical mass of the scalar field times the m Planck, and a square root of that, which is much, much lower than m Planck. So if you want to insist on those pole subtracted positivity bounds to be true, then you are forced to add operators in your theory coming in at a very, very low scale. So your naively renormalizable theory up to Planck scale, now the cutoff went really much down to this very low scale. And why is it surprising is that like this is really for any, it could be for any scalar field like in our universe. For instance, if you would have a scalar dark matter with a very low mass, this would mean that there would be new interactions at the TeV scale. And this would be true for interactions with all the possible spectator fields. So you would have to really rethink all the standard model couplings just because of these new constraints. And it would seem to be like a very high price to pay to satisfy the positivity bounds. And so we have conjectured in our work that that in low energy effective field theories with a cutoff m, with a cutoff scale m, in this case it was the scale of the cubic interactions and the mass. It could be the scale of the next degree of freedom. That if you have this amplitude in the form like this, where there is the gravity pole contribution and the next order contribution of s squared, that you could allow for a small negativity of this contribution with this scaling. And this scaling is such that if you would be able to go in the decoupling limit where m Planck goes to infinity, that this would, if you would be able to decouple the two fields, it would still demand that this coefficient C is positive, because there have been other works by Clough and Andrew where they say that the violations of the positivity, in case this really is just an order one number, they would imply the superluminal propagation in this theory, and they would not be allowed. Whereas if the scaling goes, if you cannot really decouple the gravity from the matter sector, in the sense that the processes that you're looking at are really mediated mainly by graviton exchange, then a small negativity of this type would be allowed. Let me jump to the QED bounds, because these might feel a little bit obscure. So QED by itself, when it's minimally coupled to gravity, is a low energy effective field theory. We would think it's partially UV complete at and above the electron mass. And in the absence of new physics, it could be, if it would really be the only matter in the universe, it could be UV complete up to the Planck scale at first glance. And so we will look at both fermionic and scalar QED, where in scalar QED is just assuming that the electron is a complex scalar instead of a fermion. And the results I will present mostly for the scalar QED because they are a little bit shorter, but in our work we have also done the same analysis for fermionic QED. So that's the UV theory. Like the QED is actually you can think of it as the UV completion of the Euler-Heisenberg theory, because Euler-Heisenberg theory is really like even a lower energy effective theory that you would get from QED after you integrate out the electron. And Euler-Heisenberg theory is valid that energy is well below the electron mass. And it's usually parameterized in this way. So there's the Einstein-Maxwell theory with higher derivative corrections that come as a f squared, f to the power 4 operators. And these coefficients in front of them are calculable. They have been calculated many years ago, and you obtain them, as I said, just by integrating out the electron. And they have different kind of contributions. And I'm writing this out explicitly because I will now talk about what is the scaling of those contributions and where do they come from when you think about the scattering of the electron, in fact. Yeah? And these are just the exact values of them in terms of the fine structure constant. So the scaling, both operators which we have in the IR theory, which like now are the ones that govern the 4-photon scattering, is those two. And the way they come from the QED, you can see that there are different scaling of the coefficients A and the coefficients B. And the coefficients A, they scale as knowing the exact values, they scale as the electron charge to the power 4 divided by M4, whereas the coefficients B, they have the scaling of the only the second power of the electron charge and there's also the M-Planck entering. And the reason for that is the different processes where these came from. Like if you think about like the effective vertex of the 4-4 scattering, if all the processes that were contributing to it in the scalar or fermionic QED, there were these processes. There was the exchange of electrons. Here, these are the electrons and these are the photons. So there were several kind of diagrams contributing to this 4-photon scattering, and some of them don't involve graviton exchange, and some of them do. Like this wiggly line in the middle, that's a graviton exchange. And so the processes that they call, yeah,
you have about 5 minutes.
Yeah, thank you. So the processes that contribute with the 4th power of charge, they come just from this. The processes in the top, and the other ones come from the processes involving graviton exchange. And that will be important later when we'll see what it does for the positivity bounds. Because like the IR positivity bounds, you can really easily get in the Euler-Heisenberg theory, and you just compute the 4-photon scattering, and then you bound these couplings in the IR theory. But if you write out what those couplings are in terms of the UV quantities, then you actually get something that looks very, very similar like the weak gravity conjecture. This is exactly telling you that there is a bound on the charge to mass ratio. And then you would be like compelled to say that it comes from the positivity bounds. However, that we have to, it's again a bit premature, because we have to again look at what were those different contributions to the low energy F quartic coefficients. And so these are again the same processes, and what I wanted to show is that there is the positive contribution to the scattering amplitude, to the positivity bound, which comes from those loops without gravitons. And there's the negative contributions, which come from the processes involving the graviton exchange. And what we can do now is we can use this UV knowledge. We can subtract those known positive UV contributions, which are calculable in our UV theory, with some unspecified cutoff where we can still trust our low energy theory. And the improved positivity bounds, as I said, they can do that. We can subtract the known positive contributions. In this dispersion relation, that was the original dispersion relation that we had, there were these discontinuities, which we were integrating over, and subtracting the known contributions up to some known cutoff scale would correspond to just, instead of integrating it over up to infinity, but to instead look at the integral up to some cutoff scale. And when you do that, when you really just take out these known processes, what you get from this, there's this improved forward limit bound. Here it just says that there's the original result, which was the negative result that we had for this process, and then there were the contributions from those improved positivity bounds and the finite cutoff integrals. And what you get something completely different. Now, when you look at the positivity bound, you get a bound on the cutoff of the theory. And the cutoff of QED now would seem that it is, again, it's much lower than M-Planck. And that's a very big conclusion. It happens only because we have insisted on imposing the positivity bounds once we have dropped the T-channel pole, which we didn't really know how to deal with. And so these are my conclusions. I will run through them quickly because I have a few outlook directions that I want to mention. So the main conclusion is that the positivity bounds for the T-channel pole subtracted amplitudes are violated normally, unless you want to introduce new physics at a low scale. In renormalizable scalar field theories, we found this scale, which was m with some cutoff m, which was just m Planck to the power 1/2, whereas in QED it was actually a much stronger condition, mostly because we didn't say anything about what kind of operators we want to add. We just said, let's assume we have a cutoff up to which QED is a good description, and let's impose the positivity bounds there. And it just said that to trust, if we want to insist on those positivity bounds, that this cutoff has to be very low. It didn't say us anything about what we have to add to the theory. It's just that there's a very low cutoff for QED coupled to gravity. There is the possibility to have some higher order gravitational corrections, and that they could alleviate this bound with just by contributing with positive coefficients, but this is usually, it could only happen if there are many species of particles below the Planck scale, and it would impose like very strange constraints on the mass of the electron and all the charge states in the theory. So higher order gravitational corrections, which we have neglected, like higher gravitational loops or gravitons in the loops, they could help in principle, but it would be quite artificial to impose this tight bound on the mass. And so we have like conjectured that there might be a positivity in a weaker sense once there's the graviton pole in the theory. And I'm almost done. Let me just say that there have been new works by Karen Holt, Marja Rastelli, and Simon Zafin that I am very happy to discuss about later in the discussion session, which have put bounds on similar scattering amplitudes of identical massless scalars on the higher order coefficients by imposing the positivity in the impact parameter space instead of the momentum space. And in that case, in the dimensions larger, in space-time dimensions larger than 5, you can get nice numerical bounds on the higher order coefficients without the problem of the T-channel pole. And there are many other directions that I'm happy to discuss, like one can use full crossing symmetry to have many more bounds. One can take more subtractions from the amplitude. One can think about the positivity bounds on ADS amplitudes, and there are many applications involving the modern amplitude methods like double copy and spinor helicity formalism, just to make it easier to compute the amplitudes. Thank you.
Okay, thank you very much, Lasma, for your talk. We have a couple of minutes for a quick question. If anybody has a question, please raise a hand. I will see. Okay, yeah, I see that there is one by Enrico, so go ahead, please.
Yeah, so it's about the conjecture, this weaker bounds that you conjecture apply to the case with the pole. So do I understand that big M is much smaller always than M Planck, and therefore that's a very small.
Yes, I'm sorry, maybe I have not said that explicitly here. It's M could be, it could be like the mass of the heavy particle. Like we can always partially complete these scalar field theories. Our original example was that we looked at scalar theory that mimics the QED behavior, and then we had something like a heavy electron, and then in that case the cutoff would be the mass of the electron. Mm-hmm. So basically this cutoff, is a scale up to which we do trust the renormalizable scalar field theory that we have, and above which we could have some higher states.
So just to make sure I understand, because I don't really work on this stuff. So this doesn't quite help solve the problem or that we were discussing yesterday, that theories that tend to have screening do not pass these positivity bounds, right? Because this is a tiny violation of the positivity bounds in flat space. Do I understand that correctly?
Yes, this will not help you with. I mean, this The problems with positivity there were mostly for the IR modifications of gravity. But this would, and there it was not even, those positivity bounds, like here we are mostly concerned about the gravity, whereas the Weinstein screening mechanism, sometimes we only discuss in the decoupling limit, where we only look at the Galilean interactions. And so there we would just, it would not involve the discussion of the gravity, of the presence of the gravity pole, because we are already in a decoupling limit where we only look at the Galilean interactions with itself. So this would not help that one.
Okay, thank you.
Yeah, before finishing, maybe I would like to make a comment precisely related to this approximate positivity. There were a couple of papers last year, first by Katsuki Aoki and collaborators, in which they proven that if you assume the Ryu behavior derived from string theory for the graviton scattering and large energies, you can actually show that this approximate positivity appears when you subtract the t-pole. And there was also a paper by myself and collaborators in which we proven that this can be extended if you include loops, which are a bit more problematic because they give you not only the pole but logarithms. And I think you can also derive this conjecture or prove it in some sense, this conjecture of approximate positivity, by using the result by Velazzini, Rattazzi, and collaborators, which was also very recent, about moments and generalization of positivity bounds. Just wanted to make this comment.
Yes. I'm sorry, I have not been very thorough in referencing the other works, because there was plenty. There were very many lately. That's why
many crazy people working on the same stuff.
Yeah.
Thank you very much.
It is absolutely true that there have been works where this this weaker positivity have been investigated in much more detail, and I'm very happy to discuss that in the discussion session.
We can talk more later in the discussion section, maybe. Thank you very much for your talk again. It was very interesting.
Thank you.
And now it's time to move to the next speaker. So Katy, please, if you can try to share a screen.
Okay, sure.
Okay, so just to start introducing you, our next speaker is Katy Clough from the University of Oxford. And she's an expert on black hole physics and especially on simulation of astrophysical objects in numerical relativity. And well, she will be talking today about signatures of dark matter in strong gravity environments.
Okay, well, yeah, thank you very much for the invitation to come and speak about my work. So yes, I'm going to be talking today about signatures of light dark matter in strong gravity environments. So the question that I'm really going to be focusing on is this one. So can we learn about light dark matter candidates by observing black holes or gravitational waves? So when I say light dark matter, I'm specifically talking about sub-EV dark matter. One of the reasons for that is when you go to sort of sub-EV type dark matter, you generally know that it should be bosonic, and it's described quite well by a scalar field on larger scales. So to some extent, as I say, what the question I'm also answering is can we learn about low mass real scalar fields by observing black holes and gravitational waves? But actually putting it in the context of dark matter allows us to be a bit more specific. We know roughly how much dark matter is around. We know some constraints on it on larger scales. So it just allows us to be a bit more specific in the conclusions that we make. But a lot of what I'm talking about will actually also apply to just generic kind of scalar fields, and so potentially modified gravity theories where they have an extra degree of freedom that's a scalar. So I'll start just by answering the question or telling you what I'm going to try and convince you is the answer to the question. So I think the answer is yes, in principle. There's definitely information about dark matter environments of black holes in gravitational wave signatures. The question is really just how strong are they? And in general, the conclusion is that they're quite weak. And so it would be quite challenging to find these signatures. But I'll try and make that a bit more quantitative as we go through the talk. So really, I'll start by giving a very, very brief background about light dark matter candidates, so really just enough to kind of help you understand what I'm then going to present in terms of results. But the main focus on my talk will be showing you the kind of dark matter structures that can form around black holes. So what's quite interesting is that we know quite well the dark matter distribution on larger scales from things like N-body simulations or from observations of large-scale structure. But actually, we don't really know that well the kind of structures that can form in dark matter on these kind of relatively very small scales around either solar mass black holes or even supermassive black holes at the center of galaxies. And so I'm going to give you just a couple of example cases, which are obviously biased to the ones that I've been working on, which are accretion of dark matter onto black holes. And then in the second case, dynamical friction of black holes moving through some of this scalar dark matter type fluid. So the point being that if we really understand the kind of structures that form, we can be a lot more targeted in our searches for these imprints in other types of physics. You know, if we, for example, think that there might be coupling to standard model matter, albeit very weak, or if, as I say, we want to study the kind of direct impact on gravitational waves from having this kind of slightly denser environment. So yeah, let me start with this brief background on light dark matter, and I very much recommend the recent review called Wave Dark Matter by Lam Hui, which you can find on the archive. So that gives a lot more detail than I'm going to give, and it's a very nice overview. So I just wanted to start with this picture that gives a kind of a sort of overview of the range of potential masses for dark matter candidates. So on the horizontal axis, you've got masses where at the kind of left-hand end, you're talking about particles, which are sort of ultimately bounded really by the Planck mass, although actually, you know, a bit lower than that. And then going up to more macroscopic objects like primordial black holes on the right-hand side. And the vertical line is supposed to indicate sort of what fraction of the dark matter is in that candidate. And so most of the candidates at this end, at the kind of low mass end, are still allowed to be all of the dark matter. So all of the dark matter could be a light scalar. And equally WIMPs, you know, which are another sort of well-motivated candidate, could still be all of the dark matter. That's not to say that they are, you know, you could also have a mixture of all these different types of candidate, but generally the scenario I'm sort of talking about and have in mind is a scenario where, you know, all of the dark matter is just one type of a scalar particle, which is obviously an oversimplification potentially, but makes it just a bit easier to think about. So yeah, there are a lot of theoretical motivations that I won't go into as to why you might want light particles at this kind of low mass scale, but just to say that there are some. And so really the question comes down to, you know, can these light particles actually have a cosmological evolution that results in, you know, the structures that we see on larger scales in our galaxy, you know, in our universe today. And it's been shown that actually they can. So sort of naively, you might think, oh, light particles, you know, like neutrinos, tend to be warm dark matter, and therefore they can't, you know, behave like cold dark matter, which tends to match observations better. But it turns out that for this particular class of dark matter, where you have a particular formation mechanism, it can behave on large scales as cold dark matter. So this picture is kind of illustrating that. On the left-hand side is a simulation that was done with what's called generally fuzzy dark matter, which is very light scalar dark matter. And on the right-hand side is a more traditional N-body simulation with cold dark matter. And what you're supposed to see is that these pictures look very similar. This one's a little bit smoother. And that comes from the fact that you get this kind of pressure smoothing on smaller scales, where you have this wave-like behavior in the dark matter. So the kind of the summary is, we can get the same structures on larger scales, and where we see the differences is actually on smaller scales then. So that's why, as I say, looking around black holes, you can very much sort of see the difference potentially for these light to dark matter candidates in the kind of structures that you're forming. So yeah, I've mentioned a few times that this light dark matter has a wave-like behavior. It's well described as a classical field that obeys the Klein-Gordon equation. So it exactly, as I say, has a wave-like behavior where the mass of the particle effectively sets a kind of natural wavelength for the wave-like behavior of the fluid. And so I will tend to show pictures of the scalar field itself. But it's always nice to kind of go back and forth between the picture of the scalar field and this kind of physical properties of the fluid as a whole. And you can always recover from. So here's a picture of the scalar field with this is a radial coordinate around a black hole. So the black hole's here. Oh, I don't know if you can actually see my mouse. Can you see my mouse now? Maybe you can. So yeah, so this is the black hole here, and this is the scalar field. And so if I click, it will move. So this is what accretion looks like in the scalar field picture of dark matter. So I think it's really intuitive. It's kind of easy to see that this is a flow onto the black hole. But if you want to be kind of quantitative about it, the momenta are given by the gradients essentially and the time derivative of the scalar field. So anything with big gradients, has big momentum, and equally the energy density is set by the gradients plus the time derivatives plus the sort of the mass term from the potential. So that's how we recover the kind of properties of the fluid from the properties of the scalar field. And it's those things that, we observe. We observe the energy density of dark matter. We don't directly observe the scalar field. So just to kind of emphasize that picture again, what about cold dark matter? I said it can be cold. So the picture that you should have in your mind when you have cold dark matter is that you really just have this scalar field oscillating in the bottom of the potential. So like this. So in the potential space, it's just going like this, and in real space, you just have a very uniform scalar field that's oscillating up and down. And so this is actually what gives you the behavior that it's pressureless on large scales, the fact that it has very small gradients on large scales, whereas it has an energy density that's essentially set by the amplitude of these oscillations. Okay, so before I show you some results from what we've been working on, I just want to preempt a couple of questions that I kind of get all the time. So firstly, I'm going to be talking about scalar fields around black holes. And so, the terminology that's sometimes used is scalar hair. And so the question arises, well, this is actually just a minimally coupled scalar field in, vanilla gravity. It's really the most basic thing you can think of. And we know that, of course, there are no hair theorems that say that shouldn't, you shouldn't be able to have a non-trivial configuration of scalar around black holes. So how are you getting around the no hair theorems? And then secondly, how is what you're going to show me different to the case of superradiance? So potentially a lot of people in the audience are more familiar with the case of superradiance, and I just want to contrast what we're doing with that. So on the first question, the kind of formal answer is that we are using the Jacobson loophole. So basically, when we simulate the dark matter around the black hole, we have a time-dependent asymptotic condition. So our scalar field at infinity is not zero, and it has a value, and that value is not fixed in time. That value is oscillating in time. So in this quite well-known paper by Jacobson, he showed that if there was a kind of linear time dependence in the field at infinity, then that would give you a charge on the black hole from the scalar. And we don't have a linear time dependence, we have an oscillating time dependence, because our scalar field is as I say, doing this oscillation, which gives you the kind of background pressureless, constant energy density dark matter. So this is the kind of formal loophole, but I think the more simple and sort of prosaic answer to this question is just, well, this is just a kind of environment. So we know that there's dark matter, and really what we have is a black hole that's kind of immersed in this almost infinite, relative to the size of the black hole, reservoir of dark matter. So just like, the images we see here where we have an accretion disk around a black hole, we don't call this hair. It's just an environment that will eventually, decay into the black hole, and we will be left, at time as infinity, we will have no hair around the black hole. And so, we haven't really broken the no hair theorems. In the same way, what I'm going to be talking about is this reservoir of scalar dark matter, which, if you go to really long timescales, will eventually all accrete onto the black hole and leave you with a bare black hole. But for astrophysical timescales is relevant and interesting, and is still, going to have an effect and going to have a non-trivial profile. So that's the kind of. So perhaps we shouldn't call it scalar hair. I think in one or two of our articles we called it scalar hair, which was perhaps just potentially confusing. I mean, what it really is accretion of a reservoir of dark matter, onto a black hole. So then the second question, which I think is useful, is to think about the difference between what we're studying and superradiance. So superradiance, for those that aren't familiar with it, is the case where you have scattering of a scalar type wave off the black hole, a spinning black hole, which amplifies that wave. And then because it's a massive wave, it has a mass, it's trapped in the potential well of the black hole, and it rescatters. And this process repeats and allows you to build up this kind of cloud of scalar matter around a spinning black hole by extracting the sort of rotational energy from it. So the difference really here is that what you build up in that case is a bound state of the scalar field. So a bound state decays exponentially as you go towards spatial infinity. So the energy density of these bound states is 0 at infinity, whereas, as I said, we have this essentially constant energy density as our asymptotic condition. So it's really that we have in a way a very similar scenario and solving very similar equations, but a different outer boundary condition compared to the superradiant case. And as I say, that's designed to kind of simulate the idea that the black hole is immersed in a sort of large region of fairly homogeneous density of dark matter. So just to contrast with superradiance, so it's not a competition, obviously, both are interesting effects, but it's quite useful to sort of look at the advantages and disadvantages, if you like, of both cases. So in particular, you could say, well, superradiant states require a resonance in the scale. So they require the Compton wavelength of the superradiant scalar to be of a similar size to the radius of the black hole. And so that is, in a sense, a little bit tuned. You also need reasonably high spins in the black holes to get superradiance to happen efficiently. Whereas what we're talking about is, as I say, just pure accretion. There's no need to have this particular correspondence, although in general, I will mainly show cases where these scales are similar as well, mainly because computationally, that tends to be the thing that's easier to simulate. And also it does still tend to be the case where you get more interesting effects happen. For example, build up of sort of energy density around the black hole. So the case of superradiance, the scalar, doesn't have to be dark matter, but it can be, which is, kind of an advantage. I guess superradiant. So this is quite a key point, that superradiant bound states have been shown to achieve fairly high energy densities. compared to the results that I'm going to show you. So this is a very back of the envelope computation where you say roughly you can build up these clouds to be about 10% of the mass of the black hole. And they're usually contained, in the best case in a kind of region that's about 10 Schwarzschild radius around the black hole. And so you can get very roughly this kind of number of 10 to the minus 5, comparing the energy density of the scalar matter to the kind of curvature scale of the black hole. And this is the number that really, if this number is high, it's going to increase your chance of being able to detect the presence of this kind of matter. So as I say, this is the kind of number that you get for superradiance, and I'll show you the kind of number that you get for this, this accretion case. Okay, so yeah, let me now start to show you some results. So yeah, this work was mainly done by my PhD student, Jamie Bamber. He did most of the hard work. So I think I've already shown you this picture of what accretion looks like in the case of a scalar field. So this sort of wave going onto the black hole, and you can see sort of asymptotically, it's just going to an oscillating scalar. So this was the scalar picture, and as I told you, you can translate this into the energy density. And the key point in this picture is that you can see in the energy density on the right that you get this wave-like pattern. And the wave-like pattern is clearly related to the mass of the scalar particle. So it encodes something about the sort of the characteristics of this dark matter. So if in theory, you could go and fly up to the black hole and you could measure the energy density around the black hole of the dark matter, in principle you could recreate this picture and you could tell me what the mass of dark matter is. So obviously that's a bit futuristic and we can't actually fly up to black holes and measure, but we can do things like take an emery and have the emery be probing with its orbit probing the dark matter profile around a black hole, for example. So that's the way in which I said my initial answer to my question was yes. These structures that are formed in dark matter in principle contain information about the dark matter, and if they can be probed, can tell you something about it in principle. So I should say we studied these numerically, but they are actually analytic solutions of the Klein-Gordon equation in the Schwarzschild background called the complement Hoyne functions. So you can go and look them up, and they're now in Mathematica for anyone who wants to go and plot them. So knowing these solutions, we can go and work out for a given energy density at kind of some sort of spatial radius distance from the black hole. If we set the energy density there, how dense is the dark matter around the black hole, because you can see that we're getting this kind of build up as we get towards the black hole. And so you do the calculation, and what you see is that it goes as this power of the radius. And so initially you see this result and you think, wow, 10 to the 9, that's a great enhancement of the energy density around the horizon of the black hole. That's going to really help us to detect this. But unfortunately, if you then go and compare this, given a kind of typical dark matter energy density to the relevant curvature scale of the black hole, you get the second result, which is a little bit more disappointing, where the number at the front, which you're supposed to just look at the number at the front, is 10 to the minus 12. So that's compared with what I showed you for superradiance, where I said it was 10 to the minus 5. So of course you can see that you can play around with this and you can get better numbers. So if, for example, you have a overdense patch of dark matter, dark matter is not super well constrained on smaller scales. Perhaps you have an overdense patch. Perhaps the mass of your black hole is really super massive. That also helps. Or if you set this sort of region of influence of the black hole to be larger than what I've set it here, which is sort of 10 to the 6 Schwarzschild radii. And that's really set by the velocity dispersion of the dark matter generally. So you can play around with this, and you could get this number potentially up to the same level as superradiance, but this is the kind of picture that you naturally get out when you work out the numbers. So yeah, just to say as a kind of example, this is the number you look at because it affects everything, things like quasi-normal modes. So you can go and calculate the effect of this accretion on quasi-normal modes, which Jamie did in this paper as well. And it comes out to be 10 to the minus 30, which is an absolute tiny number as the sort of fractional shift in the quasi-normal mode frequency. So something else we considered was, can you also boost this by having a more realistic physical situation? So the picture I showed you originally was spherically symmetric. Everything was just accreting radially onto the black hole. But of course, dark matter has some angular momentum as well. If we have angular momentum, if the black hole has a spin, if these two sort of spins and the angular momentum are not aligned, how does that change the picture? Can we get regions, more dense regions building up? And one thing that's quite interesting with the scalar dark matter is that if you want to give it angular momentum, it's kind of quantized, in the same way as the kind of the hydrogen atom picture, where you give it angular momentum by basically setting spherical harmonics in the scalar field profile. And we'll see that that leads to an interesting consequence when you look at gravitational waves. So it's kind of the picture you'd expect. Essentially, if you give the scalar angular momentum, you reduce the accretion onto the black hole. So you create more of a barrier to falling in, as in the normal particle case, and you form these sort of nice structures around the black hole. So you can see this is the field profile that I'm showing. And on the left, I'm showing basically the cumulative flux over time into some sphere around the black hole of the dark matter. And so just one thing that looks alarming in this picture is that it looks like for some of the higher L cases, you're actually getting an outflux. And that comes from the fact that we're just taking a sphere here. And as you increase the angular momentum, basically the cloud settles further and further away from the black hole. And at some point it settles outside our sphere. So we actually have the matter basically being thrown out by its angular momentum. So it sort of starts here, but sort of gets thrown out as it goes round. So as I say, the picture is kind of intuitive. Also, if you look at the misalignment of the dark matter angular momentum with the black hole spin, you see that if the two are misaligned, as you expect, the kind of frame dragging on the dark matter tends to make it accrete much more actively onto the black hole. So you basically remove the energy density, you remove the angular momentum from the dark matter, and it then, as I say, the rate at which the accretion onto the black hole happens increases. So one interesting point that we noted, which is kind of obvious when you think about the way in which, as I say, these modes are kind of quantized when you have angular momentum, is that at least consider, for example, the M is 1 case, if you look at the energy density, what you see is that it has an axial dependence. So it is kind of similar. I mean, these pictures look kind of similar to the kind of superradiant case, where you have this, this quadrupole moment essentially from the sort of the cloud having two lobes of energy density that rotate over time around the black hole. So when basically the dark matter has angular momentum, then you do have potentially a gravitational wave signal just from the cloud itself going around the black hole, in the same way as you do from superradiance. So again, this is potentially quite exciting. But again, if you go and sort of work out what the numbers are, which we did, a very, very approximate calculation for typical dark matter energy densities and typical types of distances, they are obviously very small. So one potential hope for this is that you could, if you imagine that this is happening, at all at all black holes. In the galaxy, for example, you could get a superposition of signals in the same way as it's proposed that you could from superradiance. We haven't done that calculation. I think it would be an interesting calculation to do. But yeah, ultimately the signals are potentially there, but again, they are relatively weak. So all of this was a bit really just a warm-up that we were doing for the binary case. So ultimately what we want to do is to evolve a binary and to see if this kind of cloud of dark matter that builds up has an impact on the merger signal. So as I say, we know that it's going to have a very weak impact on the ring down and on the in-spiral phase because of the low energy density. But we could hope that at some level in the very nonlinear regime around the merger, we could start to see an effect. And certainly, at some level, we will see an effect. It's a question of, at what energy density would you start to see an effect? And is that reasonable in the context of dark matter? So this is kind of preliminary results that we've been working on. So you can see that there is a kind of enhancement in the energy density between the black holes. Well, that was a bit quick. Let me run it again. So again, we start from a situation where we have a completely homogeneous distribution of just oscillating scalar field. And we see that over time, we build up this kind of overdense patch between the black holes. So it does seem, as I say, like you're building something up. So actually, this is something, I don't think Helvi is going to talk about this next week, but it's something that Helvi has been working on with one of her students, Giuseppe Ficara, whether there's a kind of resonance when you have certain matching between the scales of the binary and the scales of the scalar. And I think generally what we've both been kind of finding is that that's not so much the case. There's not a strong resonance, but you certainly do get an enhancement in the energy density around the binary simply from the effect of the dark matter kind of falling into the potential well of the two black holes. So we've been trying to use very sort of approximate Newtonian simulations to try and characterize this, because with full numerical relativity, we have a limit on how long we can do the simulations for. We can only do really 10 or so orbits before we actually get a merger. But you can do the same kind of thing with Newtonian simulations, and actually you find that you get similar types of patterns to what you're getting in the full numerical relativity case. So this seems to be quite a good guide to perhaps the initial conditions that we should be putting onto the black holes. So yeah, so future challenges and opportunities for this is really the last thing I mentioned, trying to get well-motivated initial conditions to be able to do full numerical relativity simulations from a kind of natural as possible an initial condition for this kind of scenario. The opportunities, so once we have this, it's kind of easy to extend it to, for example, Proctor fields instead of scalar fields, considering the impact of self-interactions or a slightly harder impact of interactions with standard model type of matter. The real challenge here is I think, degeneracies with other effects. So even if we see an impact on the merger signal, can we really distinguish that from parameters of the binary or, astrophysical environments, things like that. So this is very much, a first step in trying to understand what the impact could be. And then, you have to do all this other work to try and untangle it from other things. Okay, I think I have 5 minutes to run quickly through the case of dynamical friction.
Yes, yes. Around 5 minutes, exactly.
5 minutes, okay, perfect. That should be fine. So in this case, as I say, the work was done by another PhD student at Oxford, Dina Trekova, who is moving to the group in Potsdam from October. And she's done this nice work on considering dynamical friction with this type of scalar dark matter. So dynamical friction, just to recap, is when you have a larger object, let's say a black hole, moving through a fluid or particles, and you basically build up a kind of overdensity behind the black hole. And you can show it in this kind of schematic way. You basically have an overdense patch behind the black hole, and this creates a drag force, a gravitational drag force on the larger object, on the black hole. And so in the Newtonian picture, you can just go and basically integrate over the fluid elements of this overdensity to try and find this drag force. In the relativistic case, which I'm going to talk about, you obviously can't do this calculation because you don't have a well-defined gravitational force, but you have the equivalent, the volume integral obviously has an equivalent surface integral, and provided you're taking that surface at a large distance from the black hole in the system, this carries over into a full GR case. So essentially what we measure in the simulations is this sort of flux, the net flux of the momentum across the surface that surrounds the black hole. So we have a kind of good idea of what we're aiming for. Firstly, from this work by Lam Hui and collaborators, where they worked out what the dynamical friction force was like for this scalar dark matter. And the expression is here. Essentially, the key point of this work was to say that the dynamical friction is actually suppressed in the case of this scalar dark matter compared to normal heavy type dark matter. And the kind of motivation for this is essentially, again, something I mentioned at the beginning, basically using MRIs to probe these clouds. So for example, this paper by Otto Hanneselka and collaborators was looking at this effect, but they mainly focused on the impact of the gravitational back reaction of having this scalar cloud onto the path of the MRI, so into the dephasing of the MRI. And they didn't take into account the effect of dynamical friction, whereas that should also play quite a significant role and could potentially, enhance these effects. So our goal was to take Lam's result and essentially make it relativistic, so to test it at relativistic velocities. And we had, again, a rough idea of what we thought the correction should be. Actually, some work done by Enrico, which may be familiar to him. It was from a little while back, looking at dynamical friction in a collisional fluid. And you have these two corrections, one essentially an overall relativistic correction, where the gamma is your boost factor. And then you have another correction for the pressure of the fluid. And so I'm sort of illustrating these here. In the case of the scalar dark matter, you actually don't have a well-defined equation of state. So you actually have a velocity dependence for the pressure contribution if you make a kind of back of rough calculation for basically a wave. And so we could basically work out roughly what we thought the answer should be. And then we went ahead and did the simulations. So thanks to Yosu for making this fancy movie for me, where we basically simulate the black hole moving through a cloud of this type of dark matter, and then we wait for a kind of steady state, and we measure off basically the force on the black hole. And the result we get is in a sense maximally boring in that it matched almost exactly to within the error bars this sort of approximate analytic result that we expected based on these approximations about the pressure of the fluid. So that's, that was quite a nice result. And again, I'm running out of time, so I'll just say again, very similar to before, we can now extend this to other cases. We have to consider degeneracies with other effects. This is the kind of the future work to be done. Okay, so again, to remind you of my question, basically the sort of long answer to give is light dark matter environments can create distinctive structures around black holes, which contain information about the mass of the particle and potentially its spin and self-interactions as well, if we were to include those in our simulations. And we can potentially probe these with black hole merger signals, although the signals are quite weak. and we need to consider degeneracies with other effects, the information is in principle there. So I'll stop now and take questions.
Thank you very much. It was a very nice talk. We'll have a few minutes for questions for sure, unless people want to wait for the discussion session. You can raise your hand if you want to ask. Okay, yeah, we have 2 questions. The first one is by Kalyani Mehta. You can unmute.
Yeah, so I have one small question. I think it's not that related to this topic, so this talk. So my question is there any way that gravitational waves are interacting with dark matter? Do we have any observational indications regarding that?
So I think the answer is, it would be a very weak interaction. So gravitational waves generally interact very weakly with all kinds of matter. So of course, gravity does interact with dark matter. It's the one thing we know that dark matter does interact with is gravitons. So there is certainly some effect, but it would be very, very small. I don't know if anyone else wants to comment more knowledgeably on this topic, but I think that would be my answer.
Thank you. Thank you very much.
Okay, we have another question by Avery.
Hi, so that was a very, very interesting talk. And, I'm especially curious about this light dark matter or scalar dark matter drag. So would this not be something that binary pulsar studies might be able to go after just simply by having so many more cycles and an ability to resolve much smaller modifications of the orbital dynamics?
That's a very interesting question. Yeah, right. So in principle, yeah, it applies to any kind of compact object moving through the dark matter fluid. So I absolutely don't see why. I guess the motivation that kind of drives this looking at an emery, a smaller black hole in spiraling into a larger black hole, is the idea that the scalar cloud has built up via superradiance or something like that. So you're right that in this case we have a different kind of motivation. So why not a dark matter cloud rather than a superradiant cloud? Yeah, I don't know why. I see Diego has his hand up, so he might, being an expert on this topic, might be able to say something more useful.
Well, hello. Well, indeed, I think Diana is also in this meeting, and she's going to talk about this next week, I think. But yeah, there has been studies of trying to detect the dark matter environment from the dark matter halo in binary pulsars. And
yeah, I don't think it's using dynamical. It's not using dynamical friction, right? It's using kind of the oscillations from the background. Is that right?
Yes, oscillations from the background. And if you discover a neutron star binary system, that would be, of course, fantastic for this also, to try to see if the cloud affects the dynamics of the system. But yeah, then I think that Paulo wanted to say something. So
yeah, I was just going to mention exactly the work that Diego and Diana Lopez Nasir have done. So yeah.
Okay. Fine, thanks. Then I think it's a good time to stop for the break. And then we will have a discussion starting in exactly 15 minutes. So at 20 to 5 Rome time. So what? Take your time, go for coffee, or depending on the time of the day where you are, maybe a beer, or I don't know, and see you in 15 minutes. Ciao. And thank you again for your talk, Katy.
Thanks.
Okay, so hello again. We are back. Thomas, are you around?
Yeah, I'm here.
Okay. Hello, how are you?
Hi.
Okay, fine. So let me introduce you. Now we have the discussion session, which will last for 40 minutes. And our moderator, thank you very much for helping us with this, is Thomas Sotiriou, who is a professor at the University of Nottingham and very well known for his works on modified gravity and black holes. And the room is yours.
Thanks very much, Mario. I hope you can all hear me. So I was asked to moderate this discussion, and I was told that I should keep it as informal as possible and prepare very few slides, if any. So I went for the if any option, and I didn't prepare any slides at all. So instead, I'd like to ask you to turn on your camera, if that's okay, so that we can all put gallery view on and start feeling that we're all in the room together. So instead of slides, I've thought about, try to reflect a bit on the talks I've seen. I wasn't able actually to follow yesterday's talks because of teaching commitments, but I looked at the slides and tried to read the abstracts to see what was said. And I prepared some questions based on, some questions that popped into mind, which are quite general. But before I go into that, I think I should just open the floor to anybody that has questions to the speakers, more questions to the speakers from today or from the previous days. We also have a lot of the speakers from the previous day here. So please, come forward if you have any more questions, and or you want to continue the discussions that started before the break. That will spare you from trying to listen to me, pretending that I have something profound to ask.
Maybe I can ask a question to Katy. I wanted to ask it before I didn't have time. So is there a reason to believe accretion or dynamical friction in this fuzzy dark matter scenario is enhanced with respect to the normal, WIMP dark matter? Or why is that, if so?
No, I don't think it is enhanced. I think actually it's suppressed relative to the normal dark matter case. So yeah, sorry, I rushed through sort of that part of my talk a little bit to finish on time. So essentially, Lamb's paper, where they calculated the dynamical friction in the non-relativistic regime, showed that overall the force was suppressed compared to the sort of WIMP dark matter case. But then we wanted to basically see how that changed in the relativistic regime, so to see sort of for the final orbits where you are getting more relativistic speeds, whether it was enhanced, as I say, relative to the under enhanced scalar case, if you see what I'm saying. So yeah.
Yeah, I do. Okay, thanks.
Can I understand that suppression just in terms of the inner scale and the dynamical friction calculation that for the scalar dark matter, that's going to be the wavelength of the particle and therefore about the mass of the more massive black hole, and I don't get the large enhancement of going all the way down to the smaller object?
Yes, I think that's a good intuition for it. So essentially you have this kind of pressure on sort of large scales relative to the black hole, and that tends to smooth the dark matter out relative to the black hole. So you don't get this kind of sharp accretion, you get a much smoother profile. Yeah.
So Katy, I also had a question, which is a rather naive one. So what's the role of the horizon in the accretion scenario?
Yeah, this is actually an interesting question. So, I mean, certainly on the scales on which we're simulating, it's a perfectly reasonable assumption to say that, asymptotically, you're going to a sort of homogeneous dark matter distribution. The way you should really think of it, I think, physically is, each black hole has a kind of region of influence where it's going to accrete, from which it's going to accrete dark matter. So at some point distant from the black hole, the dark matter is not going to flow into this black hole, it's going to flow into this black hole over here, or this, this compact object. So what you're really talking about, so there was a point where I was showing the kind of the densities you get, and there's a radial scale in that. And that radial scale is basically the sort of region of influence of your black hole astrophysically, where, you know, that's the region that you're accreting dark matter from. And that's kind of set by the velocity dispersion of the dark matter. So it's larger if the dark matter is moving more slowly. Yeah.
But I mean, does it have to be a black hole? So what would change if I would replace the black hole, say, with a star or a globular cluster or whatever else?
So I think it does change things. So essentially, because you don't have the same inner boundary condition. So for the black hole, you have a purely ingoing boundary condition at the horizon, whereas for a star, you know, you have a potential. So you can get kind of, I mean, we did, actually Helvi has done more on this. I don't know if she's around. They did some simulations with stars rather than black holes. And I think when we did it, you can basically get kind of waves that kind of come in and sort of go out again. Whereas in the black hole case, you know, they always have to kind of accrete onto the black hole. So okay, from a large radius, you probably couldn't tell the difference, but on the smaller scales around the black hole, I think you can. You know, there's definitely a difference between the two cases. But yeah, I mean, you could equally look at the kind of structures that form around neutron stars, for example, and that would be interesting.
I mean, the reason I'm asking this is that, I mean, I intuitively kind of understand that obviously the boundary conditions will be different, but I don't understand. I mean, I don't have an intuition of how that actually changes things like the density, the enhancement in the density, which I guess is the main, especially if you're thinking of the Emery kind of in the Emery case. Obviously, the Emery would be around black hole if you're looking at LISA, but you know, you could think of other scenarios where we could actually probe with something else what is happening. Even the dynamical friction scenario later on, you think of something big moving into the galaxy. So I don't know. Is there any understanding of how does that affect the density? I mean, how crucial the presence of a horizon is for some enhancement in the density?
So I see that Pedro has his hand up. So I don't know if he wants to comment on this point.
Yeah, Thomas, so I think that's a really good question. And I think we actually looked at this to some extent. We were trying to find a fast way of simulating this without doing numerical relativity. And so we basically constructed a binary with Newtonian potential, okay? And only on very small scales is this different, but on the large scales, you pretty much recover exactly as you're saying, what is the effect. So I mean, it's just echoing what Katy has said, which is I mean, only on small scales it makes a difference. And, you know, if you started looking on small scales, you'd have this reflection. But on the larger scales, and large is down to not very many Schwarzschild radii, it looks perfect. You know, you get it fine. So it's not that important for how the density is evolving. Yeah,
that's right. Yeah, sorry. When I say large scales, I'm only thinking in sort of simulation terms, which is like, you know, towards the edge of, you know, 100 Schwarzschild radius even. The Newtonian case looks very similar in a way to the black hole case.
So would that then have any consequence or things like, you know, dark matter halos around galaxies or very large structures? I mean, would there be any enhancement there in the specific dark matter scenario with respect to the profile I'd get through you know, cold dark matter?
I guess it depends on the mass exactly of the scalar. So I mean, this has been proposed in the context of, you know, this fuzzy dark matter. The wavelength of your scalar is kind of parsecs in size. So the proposition is that one sort of big coherent state is your whole halo. And on that case, if you put like small individual black holes into that big halo, they don't tend to sort of interact they don't change the structure of the halo that much. So you need this sort of similarity of scales to be able to change the dark matter structure, if that makes sense. So yeah, you tend to get a sort of build up where the wavelength of the scalar is sort of similar to the size of the black hole. Where it's much, much longer than the size of the black hole, you tend to get a very homogeneous distribution and it doesn't have much impact, if that kind of answers the question.
Sure. Anybody else that wants to ask any question? I mean, I don't want to abuse my moderator role, keep asking. I mean, also in the question that was asked right before we ended the session, I think again, the situation with the emery, I guess, as opposed to the pulsars, was basically the enhancement of the density, right? The fact that the logic that in certain cases you expect to get enhancement of the density near a supermassive black hole, and then you would look at emeries, whereas in the general case, you're just probing the ambient density in the case of a pulsar. So if this enhancement is significant, did I understand this right? Was that the point, basically, looking at emeries with respect to binary pulsars?
Yeah, well, yeah. So someone on pulsars should talk about their work, but yeah, in the case of the emery, the idea is that you're relying on some kind of overdensity in the cloud, so like the superradiant cloud. And also for the superradiant cloud, you also have the additional knowledge about the structure of the cloud, so that it has some particular profile that the small object would probe, which actually gives you a bit more information about how you expect the orbit to dephase. In the case of the pulsars, I think they're mainly looking just for this, as I say, to detect this kind of background oscillation and the effect of that background oscillation in the kind of the pressure on the propagation of the signal. But as I say, probably Diego or someone like that can comment. And I think, yeah, Diana is speaking about that later.
And Enrico, you heard now.
Yeah, I just want to say, if that's the motivation, however, you may want to look at like LIGO binaries, and because especially the low mass ones have a long spiral, and with LISA that would be observed for even longer. And in fact, you can put very loose constraints using on accretion and dynamical friction from baryonic matter using LIGO binaries, and with LISA, those constraints will become even stronger, if that's the motivation for not looking at pulsars. I mean, in this case, you would have spinning black holes probably, and therefore you would have the clouds as well.
I mean, if I saw the formula right, though, I mean, in the case, not in the superradiant case, but in the case of accretion, right? I mean, because there was this dependence on the mass of the black hole, and there was this 10 to the 9 solar mass in the denominator, and what you saw, I guess the candidate is much larger black holes where you get a better.
I don't know. It depends I mean, at least for baryonic matter, and that's not the case. For instance, you need LISA, but with LIGO binaries, LIGO-Virgo binaries in LISA, you can put constraints on the Eddington ratio of the accretion. So I don't know what's the Eddington ratio of the accretion here. What in solar masses per year? What's the typical accretion rate you get? But certainly for baryonic matter, LIGO binaries work as well as supermassive binaries, I would say, or supermassive black holes.
So I think what Thomas is saying is right. Generally, so it comes back to the density that you get relative to the sort of the curvature scale of the black hole, and that is generally better as a ratio in supermassive black holes. But it's interesting what you're saying, and yeah, I will.
And there are a few papers about that, Toby et al., where this is done, in fact. So essentially what you're saying is that if I compute the Eddington ratio from the accretion rate m dot over m for fuzzy dark matter, that becomes lower as the mass of the black hole goes.
Yeah, exactly.
But I think there are also different effects, right? Because in the one case, I think you enhance the density, and when you look at the M, I mean, maybe I have misunderstood it. When you look at the M3, you're basically looking at you can look at dynamical friction, for instance, which is what you were talking about, on top of what the other people looked at. Whereas, I mean, if it's comparable mass, I mean, there's different effect. I mean, there's different dipolar emission basically for what they're capturing, and I'm not sure I understand how that these two compete with each other. So you might be able to get comparable constraints from the two different black holes just by looking at different properties of the binary, I suppose. I mean, I'm not sure I understand it fully, but which one would be better?
I guess I would. Okay, I don't know, but I think that in general, the dynamical friction adjustment, although it will kind of enhance overall the dephasing. The key effect will come from basically the change in the metric. So the fact that the metric is different, and therefore you change the sort of the gravitational wave emission, essentially. So I think that will probably still be the stronger effect, but having the two effects, and I think also the point being that when you have the two effects, if you know how both of them should evolve over time, it gives you a stronger constraint. You have more information about what you expect to see, and you can fit better, any potential dephasing that you do see, if you account for both effects.
I don't see any other hands. Oh, Avery.
So is there also going to be a suppression of the gravitational wave emission relative to the mass of the system? Because by puffing up, if you put a substantial amount of mass in this cloud, you're puffing up one of the objects, right? And if you puff it up past the orbital separation, you're modifying the quadrupole moment, right? So it's, if you had an independent mass measurement of the system, you could make a prediction for the amplitude of the gravitational wave emission, and then you could compare that to what you saw. And wouldn't this change that then, right? This would be suppressing. So you should be able to see this directly, right? Just as looking at the amplitude of the gravitational wave emission. Does this suppress that at all?
I mean, my feeling is that it would be a small effect, as I say, apart from at the point of merger. I mean, you really have very, very low densities. So yeah, I mean, you're right. Okay, the whole mass of the system would be bigger, and okay, it's low density, but overall, when you take it at a large radius, the overall mass will be different. John has his hand up. John, you need to unmute.
Right, I'm now unmuted. Sorry.
Yeah.
I'm not understanding how it is this stuff works like cold dark matter. Because you made a comment about that.
Yes.
And I'm missing the point.
No, you're not missing the point. So it's really it's a really good point. So it doesn't start in thermal equilibrium with everything else. So the proposition is that this forms from what's called the misalignment mechanism, where basically you have a sort of Mexican hat potential, and your field is sitting at some point around the rim of the Mexican hat, and at some point you get a symmetry breaking, and you tip the hat, and wherever your field was, around that hat kind of sets your initial amplitude of the oscillations of the scalar field. But if this happens prior to inflation or during inflation, then you basically end up with that same value everywhere in the universe. And so you end up with an initial condition that's very homogeneous in terms of the field. So it basically has no momentum initially, and it's formed in a very cold state. And then because it's not coupled strongly to baryons or anything else, it doesn't kind of get hot in the same way as neutrinos and things like that would. So it's this kind of, special formation mechanism. But at some point, even that won't help you. So if you go to very light candidates, then you end up still having problems trying to get the right kind of structure formation. But it's at like 10 to the minus 22 eV or something like that.
Okay, thank you.
Does that sort of answer? Yeah, as I say, it is.
It's a good funny sort of dark matter.
It is a funny sort of dark matter.
It doesn't behave as you'd expect particles to behave.
Yeah, exactly.
Do we have anybody else that wants to ask a question, both to Katy or also Lasma or any of the speakers of the previous days? Okay, if not, then I'm gonna start going through my run. So I mean, we had some fantastic talks so far, starting with summarizing current and future observations and constraints, going on to how you can actually avoid them and, you know, build theories or have theoretical constraints on your theories. And you know, today we also saw some specific scenarios for, you know, going beyond general relativity. And one of the things I've been, you know, that has been bugging me a bit is that I got a kind of mixed feelings from people. I got a lot of optimism in the sense that we're going to get better observations and things will improve and we're going to get better constraints and so on and so forth, especially from the kind of observational front. But, you know, there's also a little bit of pessimism, I think, for many of us. So I kind of wrote down the question, now that we're getting more observations, especially in the strong gravity regime, is this the beginning of the end for beyond general relativity, or is it just the end of the beginning? And perhaps maybe people can comment on that, especially the speakers, of how do they feel about the future? Are we kind of ruling out everything very soon that makes sense, and we just go back to just doing calculations in GR, basically, and improving precision and doing astrophysics or whatever else that might seems very sensible? Or are we about to invent new models and go further?
So Thomas, that's a, you know, sort of an existential philosophical question. I am reminded of a quote that comes up repeatedly now in my days, and that is, plans are useless, but planning is essential. And it highlights the importance of thinking systematically about what your options are, even though none of the options that you're going to come up with or the plans you come up with are likely to actually be useful in a dynamical, changing environment. And I think this quote comes from Eisenhower, so he meant, of course, in the military context. The same thing is true in any large organization, right? Everything changes all the time, and any plan you might have is invariably wrong. But the act of planning is critical. And I would say that in some sense, modified gravity theories fill a very similar role in that any modified gravity theory may be useless, but the action of producing them is essential, because it gives us a way to assess, one, how close what we see is to our expectations from general relativity, and two, at some point, maybe not this century, maybe not this millennia, but at some point we're going to see something different. And having a framework in which to begin to interpret that, I think, is essential. So I'm not sure I look at this as negatively. You know, the experimental process is brutal on theorists, but theorists are the only way we have of coming up with the ideas for interpreting the results.
And I can probably add on this, because my background actually is particle physics. I started doing my PhD on things closer to particle physics. And I have a fear, actually, that now in gravity, we might be starting to reproduce the behaviors of particle phenomenology in the last 30 years. Just starting to construct crazy models, effective field theories, add all the operators that we can imagine, put the constant in front of every operator, measure things on the sky now that experiments are starting to be competitive with theory. Okay, we don't see anything. We just raise the cutoff and we keep inventing models and basically spanning the infinite zoo of theories that we can build, that at the end of the day we learn nothing. So I have a fear that I'm very pessimistic, but I have a fear that we might be actually driving this direction.
I like it how the first two people that spoke, I think, so you know, took that completely opposite directions on the fence, basically. So anybody that wants to reconcile these views? I mean, you know, there are. We heard about potentially designing, catching on from what Mario said. I mean, we saw about kind of designing theories, and you know, yesterday, as I said, I wasn't here, but I understand that there was a discussion about screening mechanisms and whether we can make it work, whether we can make them work, and so on and so forth. And clearly, we can design theories that evade the constraints that we're getting. So, but potentially, we might be able to push that perpetually into the future. And obviously, all observations have finite accuracy. So if you're willing to accept smaller and smaller deviations from, you know, the standard model of anything, you can keep entertaining the thought always, you know, that there are corrections and try to find a way to describe them. I mean, you know, there are approaches like a theory kind of led approach, like for instance, today we heard Katy talk about dark matter. So the whole thing was underpinned on some light particle that is dark matter. But she also said at some point that, oh, that can be just a scalar field, which doesn't represent dark matter. And in fact, I kind of feel that, you know, if you go some years or decades back, if you were contemplating the idea that you have such a light scalar particle, basically, it just wouldn't be interesting, because you'd think, oh, why do I have so small masses? Then now that we kind of came up with some models where these kind of masses look natural in some sense of the word, you know, we find that interesting, and we're looking for these candidates. I mean, there are phenomenology-led approaches like the ones Mario was alluding to, perhaps, where you say, and you know, you can go very far. I mean, you can go even towards the kind of you know, looking under the lamppost approach, where now we're saying we have observations in these scales. What kind of model can produce deviations? Can I go and look for them? They both have pros and cons, right? I mean, our theory-led you know, developments, basically sticking to something that you think that is very well theoretically motivated, you know, is in a sense very, very prejudiced. In my, you know, you can call it theory prejudice, and I'm sure we can debate for long whether our theory prejudice is correct. I mean, you know, we heard earlier about positivity bounds and so on and so forth, and you can go and nitpick on the assumptions and say, oh, should I actually buy that? You know, and I think it's kind of clear that the truth lies somewhere in the middle, that we want to have a dialogue between theory and observations. But perhaps an interesting question to ask here is beyond general relativity, kind of modified gravity, or whatever you call it, is it expected to solve a problem, right? So am I supposed to be considering models where they explain dark matter, they explain dark energy, or, you know, and if they don't work, you know, if my model doesn't work, then I stop looking? Am I just parameterizing the unknown, which I think is what Avery was alluding to, right? And maybe people want to comment on that as well. I see Eugene already has his hand up.
Yeah, I mean, I think referring to the point about, you know, like searching for theories under the lamppost. I mean, I think this is a general problem, right? I mean, all the fields in inflation, we have the same problem. Particle physics, there's always just so many more theories. In fact, I slightly worry about not enough people to work on all the possible theories, right? In terms of whether or not it's worth doing or not. I remember having a conversation with Ichiro Komatsu, which sort of like now stuck on the back of my mind, because it has such an impact on me, right? So I remember I came up with some idea, I calculated it, it was completely crazy, and I told him, say, you know, Ichiro, this is a crazy idea, it's crazy value, it's not nobody ever going to observe it. I don't want to publish it because I don't want people to think I'm crazy. People already think I'm crazy, but okay. But then he said that, you know, Eugene, you should stop worrying about this. Just publish it. You know, you are a theorist. You should calculate all this stuff and let the experimentalists worry about whether or not you can see it or not. And I think that's sort of like a good lesson for at least for theorists, right? I mean, it's not for us to decide what we can see or not. It's for the experiments to tell us. And then as theorists, we should just calculate all the things that we think is interesting and let the world decide in a way. So I think, I mean, it's kind of like a lesson that I remember what he said to me, and it made me feel less crazy, if you like.
Still though, I mean, as a theorist, I mean, as you see models being kind of ruled out, and I think we will see more models or become less likely, perhaps. You know, you push the parameter space more and more and more, and you never get there to completely obviously ruling them out. Then you know, are we happy to move on, say, I don't know, to multi-field theories, for instance? You know, we're all considering, you know, currently the trend is very much, I have a field, I expect it to do something for me, like explain dark matter, and then I expect the same field to be present somewhere else in an entirely different regime with different length scales, and for me to detect it. Maybe that doesn't happen, right? And maybe, you know, that also doesn't
I think
work.
the question is not whether or not it's more complicated or more fields or more ingredients, but I think the question is whether or not those theories will teach us something about fundamental physics, right? If it's having more fields teach us something about what they can come out from, maybe we should look at it. You know, sometimes there's a sort of like a bias in the field about being simple, right? But I think the bias should be informative, that whether or not doing this thing actually inform us about the fundamental theory that this come from, not simplicity. You know, like sometimes having more fields actually can teach us more.
Right, but to contest that a little bit based on what Avery said before, I mean, if I can come up with a model with two fields that just shows that deviations are there when you have actually proved that deviations cannot be there with one field, it already kind of adds something to the discussion. So how I mean, one thing that has been discussed a lot that hasn't been discussed a lot is basically what about kind of non-locality, right? I mean, so there's this whole discussion, say, about fields around black holes, you know, that led to this whole business of firewalls and so on and so forth. And I mean, I think a lot of people would go as far as to say that, you know, black holes might not exist, and you know, the large quantum effects are, you know, near the horizon and so on and so forth. And that hints to some non-local behavior, basically, in the vicinity of black holes. At the same time, we're all mostly discussing about local EFTs here. So is there a chance that we just haven't broadened our horizons enough, and, you know, that's why we're in a standstill, basically? And is there a way forward?
Go ahead.
I was going to say that there are a couple threads that you picked up on. One is a concern about devolving into epicycles, and I think Mario also is a little bit concerned about that. And part of this stems from the unreasonable success of the particle physics enterprise, right? Every time there's an unexpected thing, let's just add a degree of freedom. There's a new particle, and that worked tremendously well for nearly a century. It also, in some sense, violates our feelings about simplicity, right? It would be nice to have a theory with one field explain all of particle physics, and I suppose that's the string theory enterprise, but hasn't been simplifying. But traditionally in physics, you know, the epicycles have been developed and developed and developed until somebody found, and this comes to the second point you were making, the correct sacred cow to gore, right? There is an assumption that has to be dropped. And once that assumption gets dropped, that the technology that has been developed in all those prior epicyclic efforts suddenly becomes utilized in a new way, right? And so you can think of a number of historical examples, you know, from Ptolemy to Kepler. You know, Kepler was trained up on the Ptolemaic system. From classical wave dynamics to quantum mechanics. As soon as the right cow was identified, then all of the wave dynamic machinery, in fact, all the classical field theory machinery that we don't teach people anymore, was immediately applied to understanding the quantum world. And so you know, those, I don't see these as problems. I see these as standard features that produce the desired result at the end once the correct observational fact is identified, which isn't the same as the correct observation being done. We may already see it and not know it, right?
Thanks, Avery. So we have about 7 minutes left, and I'd like to kind of perhaps switch the topic a bit to observations. And I mean, one of the things that I started thinking about when I was looking at the talks of the first day is, will we, I mean, observations are going to improve. Will we have the modeling precision that we need to continue, you know, in terms of deviation? I mean, you know, I remember Avery talking about how to break some degeneracies, basically some potential degeneracies. And if we're willing to accept that, you know, we're going to rule out some models, and then we're going to start looking at higher and higher precisions, basically, probably the degeneracy is going to get worse and worse and worse. And eventually we might end up starting to think, oh, you know, our astrophysical uncertainties are getting comparable to the constraints we would like to get, and so on and so forth. And modeling this will become more and more important. So is modeling kind of lagging behind experiment at the moment, and will it be a problem? And perhaps one crazy thought that came to me earlier today when I was thinking about this was, I mean, there's a lot of obviously now interest in, I don't know, neural networks, machine learning, AI, and all that stuff. Is it going to change completely the way we think about this? And instead of kind of parameterizing things and thinking of theories as a way to parameterize data and model stuff and so on and so forth, maybe in the future we're going to have 1,000 real waveforms, and we're going to use these 1,000 real waveforms to train AI to go and look at the new waveform and see if it actually is in agreement with some AI induced model from these waveforms or something along these lines, instead of actually try and then maybe find some way to compare that and see how well that AI kind of fit compares to GR or whatever else. So hopefully the people that talked about experiments might have something to add to that.
I think what you described is a null test, like the one they do already, in a sense. I mean, the neural networks, what you just described.
No, I mean, my understanding is that now we're training them on theoretical waveforms, right? So they're still biased by theory.
So could you, Thomas, clarify what would you use to train that?
So again, I haven't thought this through at all, right? So it's just, I'm being deliberately provocative to provoke discussion. But I'm saying, suppose tomorrow I have like 1,000, or 5,000 real waveforms, right? Could I actually try to train some algorithm in pattern recognition in these 1,000 waveforms using the real waveforms as opposed to templates?
Oh, I see.
And then start feeding it with new waveforms and say, do they match the same pattern? So I split my database into two, and I just do these kind of things without even biasing it at all with general relativity or any other theory.
That's reinforced learning, right? I mean, it's in the context of neural networks, this is what is called reinforced learning. So you have a network that teaches itself to fit the data without human intervention. That's how they train a network to play chess better than a human.
Sure. But my point is exactly this: that could that mean that we will stop needing to model basically things in the future, and we won't not going to care about?
No. Go ahead, Alessandra.
Yeah. So no, I mean, certainly it's an interesting idea, Thomas. I mean, at the moment, to extract the signal, we use models. I mean, except maybe the first detection that you could see the signal above the noise, even by eye.
Sure, yeah.
So we are not in that region where you would say, I just take the signal, the real signal, and without using any models. So eventually, maybe one day we will arrive at what you are saying, that the detector will be so sensitive that we will see, I don't know, 100,000 of signal, millions of signals, but we are not very close, to that situation.
But I would say there's again a philosophical question here, in that what does it mean to understand something? If I have a computer in a black box that gives me whatever answer I want, that's not the same thing as understanding. And I think we're in the scientific enterprise is one about understanding. And so model is a method for us to understand, not merely predict. So in that sense, I think that if the computer can learn it, that's great for the computer, but it doesn't help me. But there's another way that this happens. So I know that here in Waterloo we have some theoretical solid state and condensed matter physicists who use AI to try to design Hamiltonians. So they specify a given band gap or a band structure that they want in a material or some other material property. And then they use AI to try to figure out what kind of Hamiltonian would produce that. And then they try to figure out how to make that Hamiltonian, right? And it's not perfect, but it's actually been quite successful. And I wonder if that's something that could be applied in spirit here, where we say we want this effect, we want to have an impact on this scale or that scale, or we want to have this kind of dephasing or that kind. What kind of thing do I need to add to Lagrangians to make that happen? And that kind of takes us in a very different direction, where we're using AI to assist in model building, not replace model building.
Okay, thanks a lot. I think we're running out of time. So if does anybody want to add anything?
May I ask just a very naive question to Lasma, because I forgot to ask it during the talk, and it's a really silly question, but I didn't quite understand. There was a bound in your talk, Lasma, for the charge from the weak gravity conjecture, but I didn't. So that was a lower bound on the charge. I mean, and so I didn't quite understand for an astrophysical black hole what that bound would be. I mean, you know, we know that there is an upper limit to the charge for the Kerr bound, or well, not to have a naked singularity, bound that ensures no naked singularity. You have a lower bound. Is there a range of masses for which the two overlap? I mean, I didn't quite understand what the bound was. So it was mass Planck times Q over m, and I didn't quite understand for.
You mean the weak gravity conjecture
exactly,
itself? Yeah. It is not like the extremality condition. Usually is a condition on the mass, like the minimal mass to charge ratio, so that you would avoid the naked singularity. But the weak gravity conjecture is like it's a bound on.
So I thought it was, so the extremality is bound on Q over M, I thought, but I don't know how you define Q. Maybe that's what I mean.
It is. It sort of is the bound on the same quantity. Yeah. Just the weak gravity conjecture gives a lower bound on charge to mass ratio for states of some mass and charge in the presence of gravity, and it's basically. I mean, one way how to see why there should be such a bound is to see how extremal black holes can decay. Otherwise, if there would be no states with charges larger than that bound, then the extremal black holes could not decay into anything but extremal black holes themselves. It's sort of also a bound on how the quantum corrections.
I was asking, the reason why I was asking it was very mundane. So I mean, we can put bounds from observations on the charge of a black hole. So and I'm used to this dimensionless charge, which can go from 0 to 1, and 1 being the extremal limit for a Rice-Nordstrom black hole. So do I understand correctly that then there is a lower bound on this from the weak gravity?
Yeah, the weak gravity conjecture tells you that there should be.
And if so,
there should be different. I mean, like.
I think it's a bound on a fundamental particle.
Yeah,
so it says that there should be at least one fundamental particle whose charge to mass ratio is in the opposite direction than
it's not the charge of the black hole.
No, it's not the charge of the black hole.
Yeah,
it's a statement that there should be an elementary particle whose charge to mass ratio is bigger.
Yeah, so I thought it was the charge of the black hole. Sorry.
No, it can be interpreted as the extreme condition for the extremal black holes, but that's just a weaker version of the weak gravity conjecture, where those fundamental particles that there should be are the extremal black holes themselves. But not black holes in general. Yeah.
Okay, now that makes sense. Thanks.
That it's precisely because, as Lasma was saying, there needs to be something to decay into that the bound is the other way around. Because if it was the same way around, the black hole itself would already satisfy the bound.
I see. Okay. Makes sense.
Okay, I'm going to have to cut you and let Thomas finish because we are already a few minutes late.
Yeah, I think we can stop here. Thanks to everybody that participated in the discussion, to the speakers so far, and for to the organizers for putting such a wonderful workshop together.
Thank you very much, Thomas. And okay, let's start with the next talk. The next. Sorry. Our next speaker is Astrid Eichhorn. Astrid, if you can start sharing your screen. Okay, thank you. Yeah, Astrid is a professor at CP3 Origins in the University of Southern Denmark, and she's an expert on particular on the asymptotic safety approach to quantum gravity, but more lately she's been working actually on connecting quantum gravity consequences or quantum gravity phenomena with low energy observations or the low energy physics that we observe in the infrared. So thank you very much. We are very glad to have you here. The floor is yours.
Thanks, Mario, and thanks to the organizers for putting together such a very interesting meeting and for inviting me. So this meeting is about current challenges in gravitational physics, and surely one of the current but also persistent challenges in gravitational physics is to understand the quantum nature of gravity. And within that field, I think one of the most pressing challenges is indeed to connect potential ideas for quantum gravity theories to observations. Now, Katy, I haven't solved that challenge. So what I will be talking about here are sort of three directions in which I think it's worthwhile to think in, and potentially one of those will actually in the future really allow us to forge that connection. So sort of as a preface to my talk, let me just emphasize that physics in general always proceeds because experiment and observations and theory somehow walk hand in hand. At one point, the one is a little faster, at another point, the other, but ultimately we really need both in order to make progress. And in quantum gravity, that has very much not been the case. It's very much just theory-based until now. And I think this is really part of the reason why we don't yet have a universally agreed upon understanding of quantum gravity, is because we don't have a good connection to observations. And therefore, we have this sort of whole landscape of different theories of quantum gravity or proposals for theories. We also have a few sort of white gaps still remaining in that landscape. And also we don't have a good understanding of the relation of these various proposals for quantum gravity theories to each other. And so the connection to observations ultimately will hopefully allow us to do two things. First of all, hopefully it will allow us to understand whether some of these proposals for quantum gravity would just result in structures that are not compatible with what we observe. And secondly, it would allow us to understand whether some of these different theoretical approaches, which on the sort of mathematical side tend to look quite differently, whether some of these are potentially just mathematically distinct formulations of one and the same physics. So this would be about understanding whether there are universal physical consequences that come out of different quantum gravity models. And of course, the main challenge here, just to remind you all and sort of set the stage for the talk, is the tininess of the Planck length. And that, of course, comes from thinking about the Bronstein cube, where we have h bar for quantum effects, 1/c for relativistic effects, and the Newton coupling for gravitational effects. And this allows us to go from classical mechanics to Newtonian gravity to general relativity, sort of along one side of the cube, and on the other side, from classical mechanics to quantum mechanics to quantum field theory. And then, of course, the missing corner here is the one where we would have quantum effects, relativistic effects, and gravitational effects, and where quantum gravity would sit. And just based on the consideration of the Bronstein cube, we can come up with a very naive estimate of where we would expect quantum gravitational effects to set in, which is the Planck length, just arising from combining these three constants at 10 to the minus 35 meters. And the tininess of that scale, that's, of course, the key challenge in trying to connect quantum gravity to observations. And so what I would like to talk about today is sort of three ideas in this direction. The first is taking a step back from this naive dimensional estimate and saying, well, how do we actually know that is the correct estimate? There isn't any dynamical principle that goes into that. It's really just dimensional analysis. So who knows what actually the scale of quantum gravity effects, or more generally, new physics effects in gravity actually is? And what I would like to discuss is a model that will allow us to constrain the scale of new physics in black hole observations, specifically black hole images. And then, of course, it could very well be that observational constraints, once we are actually able to do that, just allow us to put an upper bound on the scale, but don't lead to any observation. And we are still left with the scenario that most likely quantum gravity effects set in at the Planck scale. And what is it that we can then, what is it that we can do then? So this is where the sort of the second and third path here come in. This is where we could still derive observational consistency tests for quantum gravity by understanding its effect on particle physics in and beyond the standard model, and also the interplay with symmetries in that setting. And in both of these settings here, it's not enough to just focus on a pure quantum theory of gravity. It's important to understand the interplay of quantum gravity with matter. So to connect quantum gravity to observations in this setting, matter is really key. So with this, let me now start with the new physics in black holes. So this image, all of us have seen that many times, including at this conference. But what is it that we are actually looking at here? I think there's one thing that we know about this, and this is that it can actually not be a GR black hole that we are looking at, for the simple reason that in GR, black holes do harbor curvature singularities, and so therefore ultimately GR does not provide us with a consistent description of the true nature of these objects. Of course, I'm not claiming here that the sort of outside of that object can't potentially be reasonably well described by a Kerr metric. I'm just saying that ultimately general relativity is really not enough to allow us to understand what this object is that we are looking at. And that, of course, motivates to then go beyond GR and look at black hole shadows beyond GR. And there's, of course, a very vast literature on that basically follows two main paths. One is to parameterize all possible deviations of the metric from a Kerr metric. That on the one hand, if you're really parameterizing all possible deviations and are not making any hidden assumptions about constants of motion and so on, that will of course cover sort of the complete space of physics. But of course, on the other hand, it's very disconnected from fundamental theory. So even if you would detect a deviation in one of the metric coefficients from Kerr, what would that really tell you about the underlying physics? Then on the other hand, of course, you can just calculate the black hole shadow in each conceivable theory beyond GR. That is, of course, practically impossible, but also it's really way too much information given that the EHT and also other black hole observations actually have finite resolution. And very likely a lot of these theories will just give rise to very similar or sort of universal observational imprints. And so therefore, I would advocate for a sort of middle ground where we take the best of these two approaches and combine that and build sort of parameterized models of black hole metrics that are based on some general physical principles. And I would call this a sort of principled parameterized approach to black hole shadows. And so what I will report on is recent work together with Aaron Held, who's a postdoc at Imperial College, that falls into the second category. And so what we did is we devised 4 principles on which we base a whole family of spinning metrics. And then we asked the question whether these physics principles that we put in here, whether these lead to any observational imprints. And the first principle is that the black hole spacetime should be described by a metric. So even in the setting where you would have some quantum gravitational effects kicking in and changing the spacetime, we still demand that it can be well described by a metric. And so then this is the metric that we are using. This is just Kerr metric in ingoing Kerr coordinates, where the mass is now substituted by a space-time dependent function. And what that allows you to do is it allows you to encode the physics, and the physics that we are looking at here is physics that leads to a weakening of the gravitational attraction in the core of these objects so that it can actually lift the singularity. So then the second principle is that the Newtonian limit obviously should be recovered correctly, simply because that's observationally quite well constrained. And that actually means that this mass function that we have in here, that should approach 1 in appropriate units as we go towards large radii. Then the third principle is where we say the new physics should actually solve the problem that GR has with black holes and lift the curvature singularity. And that actually constrains what the mass function does in the core of these objects. So it's small radii and in the equatorial plane where it has to go to 0 sufficiently fast in order to make this metric a regular one where none of the curvature invariants diverge. And so, of course, this is basically what is done in any type of regular black hole model that is written down. The new thing that we've added is that we impose a locality principle, which we expect to sort of capture some of the physics of underlying fundamental theories. Specifically, what we mean by this locality principle is that the deviations from Kerr should be set by the local value of an appropriate curvature scale. So you can think of this locality principle as sort of mimicking what you might expect maybe in effective field theory types or effective field theory ways of thinking about gravity. Now, those of you who have ever taken a closer look at Kerr know that, of course, the curvature invariants, they change their sign across the space-time. And so then it becomes a bit of a challenge to say, what do you actually mean by the local value of the curvature scale? And so what we mean by that is that we look at the independent invariants that you need to characterize Kerr spacetime, and we say that whenever any of the absolute values of any of those curvature invariants becomes larger than a certain new physics scale, this is where we would expect the new physics to kick in. And so what we therefore construct is sort of an envelope function for all of the different curvature invariants for Kerr spacetime that I'm not giving you the expression for here, but it's this quantity that you see in this plot in this red line. And the modifications from Kerr are then controlled by this product of this curvature scale times the new physics scale to the 4th power. So then you still have some freedom in the construction of these black hole models. And that brings us to a family of spinning metrics. One of those is given by this mass function here. That was actually recently proposed by Simpson and Visser in the spherically symmetric case. And I will be using this as one example here. So then these 4 principles, we then ask what type of observational imprints do they actually lead to, in particular the regularity and the locality conditions. And from the regularity condition, the fact that this mass function goes to 0 in the center, that actually means that the gravitational force is weakened, and that actually means that the object we are looking at becomes more compact. And intuitively, you can think of that as the effect that the position or the location where the light cones are sort of tilted over so that you have the horizon, that moves further inwards because of the weakening of the gravitational attraction. And so therefore, if you look at the location of the horizon of this regular object compared to Kerr, the horizon moves further inwards. And now this locality principle, that actually means that the modification is always largest in the equatorial plane, because this is where for Kerr, the curvature invariants are largest. And that actually means that the strongest effect, the strongest compactification, if you will, that happens in the equatorial plane, which is why the horizon in the regular case is no longer spherically symmetric, but actually features a sort of dent-like feature. So this locality principle, which is a principle hopefully encoding some of the underlying fundamental physics, that then has a direct implication for the space-time structure, namely a dent in the horizon. And then as a next step, we ask, are there any observational features that follow from the existence of that dent? And so what we are doing here is we are looking at this regular space-time. On top of that, we're just adding a static disk model with just a prescribed density and emissivity. And then we follow a ray tracing code to generate these simulated images. And in particular, we will mostly be focusing on this region here that is on the prograde side of the shadow boundary, because this is where most of the effects will be at. And in fact, there are then 4 effects that follow, or 4 observational imprints that follow from the regularity and locality. And I'll walk you through them now, and then I will discuss how they are actually connected to these 2 principles for fundamental physics. So first of all, here I'm comparing the Kerr case to the regular case. And this box that you can see in both images is at the same distance to the retrograde shadow boundary. And then you can see that in the Kerr case, the prograde shadow boundary is close to the left-hand side of the box, where it's closer to the right-hand side of the box in the regular case, which means that the object is overall more compact, as you would expect if you're looking at the image of a more compact horizon. And in particular, the prograde shadow boundary, this is where the increase in compactness is largest, and which is why you get this shift. Then the second observational imprint is a relative stretching of the image features, and this can best be seen if we switch to a slightly different inclination, namely the approximate inclination that M87 probably has. And so then the image looks very much spherically symmetric. And then we are zooming in into a region just on the side of the image, and you can see essentially the shadow boundary is this innermost line here, and then you see these additional rings that Avery was also discussing in his talk 2 days ago. And now if you compare the Kerr case to the regular case, you see that these rings are stretched in the distance from each other in the regular case. And again, that's a consequence of the increased compactness, because the further inwards you move, the larger the new physics effect, and the new physics effect is to produce an increase in compactness. And so therefore, this then overall leads to a stretching out of these image features compared to Kerr. Now for the third and for the fourth feature, we'll have to zoom in a little bit more to see them into this region here. So this is zoomed in more into this box. And then you can see that the shadow boundary actually features cusps, and it also features a dent here in the equatorial plane. The intuitive reason why these occur is a little bit more tricky, and let me try to give you an idea for how that happens. So in these different image points, the geodesics that arrive there, they circle around the black hole, and they trace out different ranges in the polar angle why they do that. So for instance, the geodesic that arrives here, that's this one denoted by this crossed circle. It traces out a whole large region in the polar angle, and as it does that, it probes all of these different sort of radii of the horizon. In contrast, the geodesic that arrives here actually probes a much smaller extent in the angle, and therefore probes a different effective radius. And then there are regions in the, or points in the image where you have a transition between these different ranges in the angle. And then these different geodesics sort of probe different effective radii. And then this transition leads to these cusps and also to a dent here. And then finally, the last thing that happens is broken reflection symmetry of the shadow boundary that happens if you go away from an inclination of pi/2. You can see this effect just here in these images of the shadow boundary, that there is no reflection symmetry about the y=0 axis. There's also an intuitive sort of geometric optics intuition for that. So what I'm showing you here is sort of an image or a sort of illustration of the Kerr horizon, which is spherically symmetric, and then the horizon of the regular case, which has this dent. And of course, here the effect is sort of over pronounced just for purposes of illustration. And now if you just tilt these objects to different inclinations, then in the case of Kerr, you will still have a spherically symmetric horizon and therefore a reflection symmetric boundary. But in the case of the regular horizon, you will then have this broken reflection symmetry. All right, so those are the four observational imprints that we get. And the first thing to emphasize about that is that the size of the effects depends on the new physics scale. And so therefore, this gives us prospects for new observational constraints on the new physics scale, which are just completely decoupled from sort of theoretical estimates for new physics scales in gravity, which are based on dimensional analysis. This is just a purely observational way of constraining the new physics scale. And of course, with things like the next generation EHT, this will hopefully actually open the opportunity to really put interesting constraints on that scale. But of course, you could ask whether these features here are sort of consequences of the very specific choice of the mass function that I put in. And this is the last message on the black holes that I would like to convey, namely that that is not the case, and that instead there are what you could think of as observational universality classes, that certain features in these images are directly tied to some of these new physics principles. And to motivate that, here I'm just showing you a range of different images at different inclinations. The leftmost column is the Kerr case. The right column is the Simpson-Visser type mass function that I was using in my previous slides. Then here is a Hayward type mass function. Both of those satisfy the regularity as well as the locality principle. And then for comparison, I'm showing you a mass function that does not satisfy the locality principle that leads to a spherically symmetric horizon, and that does share the first two features, namely a shift of the shadow boundary and a relative stretching, but it does not exhibit cusps or broken reflection symmetry. And so based on that, we conjecture that such sort of physical principles, regularity, locality, or other principles that you could think of, that those could be tied to specific observational features that are sort of universal for whole classes of black hole models. And therefore, if we detect features like that, that would really provide us with some information on the underlying fundamental physics model. Right, so that concludes what I had to say about black holes. I would now like to move on to sort of give you sort of two very quick ideas about what one could do about observationally constraining quantum gravity if the scale of quantum gravity indeed is the Planck scale. And so what the challenge that we are confronted with here is then that we have to bridge the gap between the Planck scale and something like standard model scales. And the sort of typical statement within the field would be that that is something that is basically impossible to do. There will be no effects that bridge that gap. And I would like to challenge that view, and I will do that based on an analogy here. So the analogy would be that instead of the quantum gravity scale, we're looking at a molecular scale, and different microscopic models that we have would just be different molecules with very different intermolecular interactions. And then as we zoom out and we go to much, much larger scales, most of the microscopic information gets lost, and we end up with something like hydrodynamics that isn't really so different at macroscopic scales and that doesn't carry any imprints on the underlying microphysics. And that's sort of the picture that we have in mind when we think about connecting quantum gravity models at the Planck scale to LHC scales, where we would expect that we just universally get out the standard model and can't make any conclusions on the underlying fundamental physics. But of course, this picture is not quite true, because it's most of the microscopic information that gets lost as we zoom out. But there are imprints of microscopic physics that make it to macroscopic scales. And one example to think of here would be the viscosity. The viscosity is something that arises directly from the microphysics, from the microscopic interactions at the molecular scale, but it's an observable that can be measured at scales which are much, much larger than the molecular scale. And from these measurements, you can then conclude which of the potential underlying microphysical models actually gave you the right value and which one would actually be ruled out. So what I'm talking about here is not sort of smoking gun tests or sort of smoking gun signatures of quantum gravity, but observational consistency tests. And the challenge then, of course, becomes to identify which of the standard model or beyond standard model couplings are sensitive to the microphysics. And I will be giving two examples, and the first will be tied to the asymptotic safety paradigm for quantum gravity. And what I would like to do here is to give you a very, very, very short introduction to asymptotic safety, or a useful way to thinking of asymptotic safety is in terms of what it actually physically means, and that is actually quantum scale symmetry. So in general, of course, symmetries are always very powerful to allow us to understand larger systems by just knowing parts of them. For instance, reconstructing the full butterfly from reflection symmetry, or the sunflower from rotation symmetry. And in the case of scale symmetry, we can reconstruct what a system looks like as we zoom in towards much, much smaller scales. And the idea underlying the asymptotic safety approach to quantum gravity really is that scale symmetry could be a much, much deeper principle of nature. Specifically, in very brief, what the underlying idea is as follows. If you look at the gravitational couplings, such as, for instance, the Newton coupling, and you look at a dimensionless version of those couplings that parameterize the strength of gravity in a dimensionless way, so the Newton coupling times an energy scale squared, then that quantity increases in the classical gravity regime. But once you reach the Planck scale, where quantum gravity fluctuations kick in, you then enter a regime where quantum scale symmetry is realized, and this dimensionless measure of the strength of gravity just stays constant no matter how far you zoom in. So that's a sort of the intuitive picture behind asymptotic safety. It is arguably the most conservative approach to quantum gravity, because it simply provides you with a quantum field theory of the metric, so no exotic ingredients here. It ties back to what I previously said about regular black holes in the first part of the talk, because sort of similar black hole metrics have been motivated from this approach. And what will be most important for the connection to observations is that this microscopic scale symmetry that we have here, that restricts the values of couplings at macroscopic scales. So let me explain the mechanism for that, at least briefly. The idea here is that beyond the Planck scale, there is a quantum scale invariant regime where the gravitational coupling, as well as different standard model couplings that I've included here, all of those become essentially constant and realize quantum scale symmetry. At the Planck scale, gravitational fluctuations then decouple dynamically and become suppressed, so that below the Planck scale, you're then entering a regime which is just dominated by quantum fluctuations of matter, and which just leaves you to essentially LHC physics at low scales. Crucially, what happens here is that as a consequence of quantum scale symmetry, the values of some of these couplings are fixed at the Planck scale. So in the technical language, those are the irrelevant or infrared attractive couplings. So in this setting, for some of the coupling constants, you do have the freedom to adjust their values and you still get quantum scale symmetry. But for other couplings, you do not have that freedom. There's only one very specific value at which you can reach quantum scale symmetry. And this is the way in which demanding quantum scale symmetry, or asymptotic safety, then fixes the value of that coupling at the Planck scale. And then you can just use the standard renormalization group flow of the standard model to then flow down to LHC scales and ask what is the consequence at observable scales of quantum scale symmetry at and beyond the Planck scale. And I like to think of this as sort of the quantum scale symmetry being the Cheshire cat that is realized at trans-Planckian scales. But then, of course, at lower energy scales, scale symmetry is no longer realized. We do have distinct scales in nature, but an imprint of quantum scale symmetry stays behind, like the smile of the Cheshire cat, in that it actually fixes or predicts the values of some couplings. And before I give you two sort of very, very short just glimpses at some of the results, let me just highlight, for those of you who are interested, the tool that is being used here, and highlight two important approximations, namely that I work in Euclidean signature, and that there is a systematic truncation of higher order terms in the dynamics, which means that the results I'm presenting are affected by systematic uncertainties. So with that, let me give you sort of a teaser at some selected results. Feel free to ask me more about that in the Slack channel or by email. So in the standard model, what we found is that there is a predictive relation that arises from asymptotic safety and relates the top quark mass, the bottom quark mass, and the electromagnetic gauge coupling. And this is a busy plot, so let me try to point out the salient features. What we have on the two axes are parameterizations of the strength of quantum gravity in asymptotic safety. And what we then have here are contour plots of the resulting values of standard model couplings that are in a band around the experimental value. These bands are significantly larger than the 1 sigma value. So within these bands, you're sort of seeing standard model-like physics. And the key thing about this plot is that the band for the top quark and the bottom quark masses intersects with the band for the gauge coupling, which means that you get a prediction, a calculation from first principles of these measured couplings, and that is actually very much standard model-like. So then to tie to one of the other big questions about gravity, namely the nature of the dark matter sector, let me show you how the same predictive power of asymptotic safety could actually allow us to learn something, at least theoretically, about a dark matter sector. So there's of course a huge plethora of different dark matter models. Let me focus on one relatively simple one, which contains a dark fermion and a dark scalar, and they are coupled to the standard model through a Higgs portal. In an effective field theory treatment of that model, the masses and the couplings in that setting would all be free parameters, and that actually gives you a huge parameter space that you would want to test observationally. And that story changes completely once you ask that that model actually can be consistently embedded into an ultraviolet completion with asymptotically safe quantum gravity. So this is relatively recent work together with Martin Pauli, one of my students. And what we found is that unlike in an effective field theory approach to that model, here you get a lot of predictions or relations between the various couplings in the model. So in this plot here, I'm showing that as a function of the Higgs portal coupling, you can calculate the dark scalar mass, you can calculate the dark fermion mass, the non-minimal couplings, which are not included in the plot, also the mixing angle with the Higgs, and finally the dark matter self-interaction. And what that means is that instead of having a huge open parameter space, if you demand asymptotically safe gravity as the UV completion, that basically pins you down to this just one line in parameter space. And that actually means that there's a way, or that this is sort of a template for how you can think of observational consistency tests for quantum gravity, specifically in this case, for asymptotic safety. Now, in the remaining, I guess, 4 or 5 minutes or so.
5 minutes, exactly.
Okay, great. Let me move to the last example that I would like to briefly flesh out how to connect or how to sort of close that gap between the Planck scale and lower energy scales. And that has, again, to do with symmetries, but in this case, it will be Lorentz invariance. So the breaking of Lorentz invariance is something that is being discussed in quantum gravity again and again. And the form that it would take is that instead of a setting without a preferred foliation and therefore with full diffeomorphism invariance, there would be a preferred foliation, which means a breaking of diffeomorphism symmetry to just foliation preserving diffeomorphisms. What that then means is that the gravitational dynamics, beyond having something like an Einstein-Hilbert term, could additionally contain terms that depend on the extrinsic curvature of your spatial hypersurface, and also on a time-like normal vector that is sort of normal to that hypersurface. And then, of course, the question becomes, how can we possibly detect whether the quantum gravity dynamics actually contains terms like these? Again, these are something that would set in beyond the Planck scale. There are, of course, possibilities to constrain those observationally by comparing the speed of light and the speed of gravity using the GW 170817 gravitational wave signal together with the corresponding gamma ray burst that was also alluded to in a number of talks in this meeting. And that is one way of actually constraining these couplings in a quantum gravitational setting. What I would like to present here is that potentially thinking about the interplay of quantum gravity and matter and the effect that Lorentz violation in the gravity sector has on the matter sector, that could lead to even stronger constraints. And that's joint work with Alessia Platania and Mark Schiffer. So as a sort of short teaser, I'm showing you this plot here from the paper that on the axis has two of the couplings from this Lorentz invariance violating dynamics. And then it does have the bounds that come from the multi-messenger gravitational wave gamma ray burst combination. And then these additional contours here are sort of projected constraints that one could obtain by thinking about the effect that this gravitational dynamics would have on photons, and then using observational constraints on the absence of Lorentz violations in photon propagation over large distances. So let me give you just a glimpse at the details of how the argument or the calculation works. So once these terms are present in the gravitational dynamics, that Lorentz symmetry breaking percolates from the gravity sector into the matter sector, and you get additional terms for the propagator of photons that are Lorentz violating terms parameterized by this coupling zeta. And in the plot here, I'm showing you the scale dependence of that coupling as it is driven by quantum gravitational Lorentz invariance violating fluctuations. So first of all, the thing to note in this plot is that quantum gravity fluctuations drive this coupling away from zero as soon as these gravitational couplings are present. It's then very quickly driven towards larger values or larger absolute values, and it is sort of being caught to not grow too large by an infrared fixed point, and the value of that depends on the gravitational couplings. What that actually then allows you to do is ask, well, what do we know observationally about that coupling zeta, which actually affects photon propagation over large distances? And from constraints on that coupling, we can then constrain the underlying values of the gravitational couplings. And so then this is what would lead us to these stronger constraints here. And observationally, actually, if you look at actual photons, I think these bounds are actually something that is being achieved in observations. And we have looked at that in a toy model where we've not looked at sort of photons coupled to the full standard model, but just sort of a subset of degrees of freedom. So you should not take these bounds seriously as actual observational bounds, but just as a demonstration that thinking about the interplay of quantum gravity with matter, you can actually then potentially arrive at much stronger constraints on your microscopic gravitational dynamics than you can think arrive at by thinking about quantum gravity on its own. This was sort of a lightning review of some ideas of how to connect quantum gravity to observations, or how to start going in that direction. Black hole observations are, I think, opening up interesting possibilities to constrain more generally the scale of new physics, not necessarily really the scale of quantum gravity, unless that is really unexpectedly large. But then constraints on particle physics are really something that allows us to connect quantum gravity at the Planck scale to observed and measured quantities at the electroweak scale. There's, of course, completely different directions also in which people think in connecting quantum gravity to observations that I've not addressed here. But I would say overall, the time is ripe in this field to really more seriously think of ideas of how various theories for quantum gravity could be connected to observations, and whether we can start ruling out some of these many quantum gravity candidate theories. So stay tuned, and thanks for your attention. And I'm looking forward to questions.
Thank you very much, Astrid. It was a very interesting talk. And now, yes, we have a couple of minutes for a quick question. Thomas has raised the hand. So,
hi, Astrid. Many thanks for the talk. So while you were giving the first part of your talk about regular black holes, I haven't thought much about regular black holes at all, but I was trying to picture in my mind how the Penrose diagram looks like. And I couldn't figure out how I should extend scribe plus past the horizon, because you obviously don't want to extend it as an infinity, because that's not an event horizon anymore. And if I extend it as an inner horizon, then that's probably unstable. So the regularity goes out of the window. So based on kind of this naive thought, I would have thought that regular black holes would just simply be unstable, no matter what you do.
Yeah, no, I mean, thanks for bringing up that question. That is, of course, an important question. So the stability of the inner horizon is something that is being investigated and sort of debated in regular black holes. But of course, the challenge here becomes that in order to investigate stability of that, you would need a full underlying gravitational dynamics in which you can say whether or not it will be stable. So this sort of goes beyond what we did here, where we just say, well, we just try to parameterize what this object would be that we can conceivably look at. And of course, within that approach, you can then not really make a statement on the stability, because you can only do that within then very specific underlying sort of fundamental dynamics. But I agree that that is probably one of the most important questions to understand about regular black holes.
I mean,
but also in let me just add that in the spinning setting, of course, it becomes much more challenging also to investigate. But that doesn't make the question less important. I
mean, I'm thinking about it in the simple, even if you put stability to one side, I should somehow be able to analytically continue the space-time. So in Schwarzschild, the singularity tells me I can continue north basically because it's space-like, right? In GR black holes, in Rise and Nordstrom or Kerr, exactly because the singularity becomes time-like, I can analytically continue, and then I get more space, and then I need more asymptotic regions, which obviously is not something that can be physical, which is exactly how we arrived to that point that there has to be some mass inflation and stability and all that stuff. So I don't understand in the regular black hole how you can't analytically extend that space-time. How does that space-time end in the interior of the black hole, and you don't just continue and create an infinitely large universe?
Mm-hmm. Yeah, no, I don't think I have a really good answer to that. But I mean, ultimately, the full space-time, of course, you would also want to understand that sort of going beyond a static setting and then really take effects of, Hawking evaporation and then the final stages of that into account. Right? I mean, because that would be the space-time and also the corresponding Penrose diagram that would be really of interest. But yeah, I don't have an immediate good answer to your question.
Sure, thanks.
Okay, we have another question, and then we will go to the next talk. Johanna?
Yeah, hi Astrid. Thank you very much for your interesting talk. I just had a question about the first third of your talk regarding the locality principle, whether you could once again comment more about how you motivated and whether you have checked that it is independent, for example, from the one to the third principle. So how the relation is.
Mm-hmm. So the locality principle is really the idea, it comes from an effective field theory type thinking about gravity, where you would say that above a certain curvature scale, you would expect that modifications from GR kick in. And that, if you take that seriously, then that would tell you that at a given sort of space-time point, you look at the value of the curvature scale in Kerr, and that tells you how large the modification is. And I think you asked also about the connection to the second.
So whether maybe the fourth does not imply the second and the third, for example.
So the fourth principle, the regularity, no, I don't think it implies that, because you could also devise regularity in a way that, I mean, you basically make sure that the very core of the singularity, that is removed by appropriate modifications, but then at every other point in the spacetime, you make the modifications sort of completely arbitrary. So these are really independent conditions. And I mean, there's lots of examples where people look at regular black holes and then use sort of a Janice Newman type algorithm to upgrade them to spinning black holes. And in all of these, which are completely regular or typically with regular solutions, some of them do have non-uniqueness of curvature invariance. But in all of these cases, you would have a violation of the locality principle. So there's lots of examples in the literature, except so in fact, probably all the examples in the literature of spinning regular black holes are ones which do not respect this locality principle.
Okay, thank you.
Okay, let me thank again Astrid for this very nice talk, and let's move to the next speaker, Toby Wiseman. You can start sharing. You're muted. Okay, fine.
Hi. Yep. I'm going to try and start sharing
your screen.
Let's see how this goes.
Okay, we can see it, so it went well. Okay, so we go back to London, to Imperial College again, and we have Toby Wiseman with us. Toby has worked in a lot of topics, conformal field theory, solography, formal QFT, black holes, and today he will talk about the spinning black holes in Einstein ether theory. So thank you very much. We are very glad to have you here, and it's your turn.
Thank you very much. So I like black holes the best, I should say. I hope you can hear me. Is that right? You can hear me okay?
Yes, it's okay.
Great. Okay, so I'm going to tell you about rotating black holes in Einstein ether theory. And this project actually has a somewhat long history. So hopefully the paper will be out very shortly. But perhaps you shouldn't trust the month when I tell you that it actually started off with my student Alex Adam and Pau Figueres, probably around 2013. And we looked at a numerical construction of these rotating black holes in Einstein ether then. And we found we got it working and so on. And in fact, you can find details in a 2014 PhD thesis of Alex. And then we talked to Ted about it, and we said, well, I mean, we talked to him about it. He said, oh, you should write it up. And we never really got round to it, partly because we never really knew what to say about the solutions. And actually, it's only more recently, particularly with the LIGO and neutron star constraints, that I think there's a nice story. And so we've got together with Ted, and hopefully this paper will be out shortly. But as I say, it's been a little while in the oven. So my interest really originally was trying to just understand how to numerically construct black holes in this theory for reasons that I will make clear later. It's a very interesting sort of theory. There are classes of theories like it, where constructing stationary black holes is much more challenging and needs some novel techniques. However, it turns out that they actually have a very interesting phenomenology when you look at them. In particular, when you look at them in the phenomenologically viable range, given the current constraints on Einstein ether. Okay, so I'm going to try and tell you about that. But basically, the goal is to, in some sense, through the lens of black hole physics, try and understand the nonlinear behavior of Einstein ether better. So I'll start by telling you about black holes and theories with multiple wave speeds to try and tell you why Einstein ether is interesting. And then I'm going to give a brief review of Einstein ether. There are many people who are far more expert on it than me, and in particular on the observational constraints. And then I'll talk to you about how to numerically construct stationary black holes, and in particular in Einstein ether theory. But given the time constraints, you're probably pleased to hear I'm not going to go into gory details, but I'm happy to answer questions on them. And I'll tell you then a little bit about the results of some black holes that we find. And in particular, and in some sense, this is the most important part, for viable Einstein ether theory, we'll see that we actually recover Kerr-like behavior for these black holes. And I'm going to explain why that happens, why we think that happens. Okay, and this is actually a more general story than just applying to stationary black holes. Okay, so black holes with multiple wave speeds, in theories with multiple wave speeds, are interesting. If you haven't thought about it, it's potentially confusing because you might think, well, hang on, I've got wave modes with multiple speeds. Surely they must have different horizons. So for example, supposing I look in some higher derivative theory, maybe with a scalar, but still with second order equations, I will potentially have different modes with different wave speeds other than light. Surely they can't agree to have the same killing horizon for a black hole. But actually that's not true. And generically, I would say you should expect all these modes to agree to have a common speed, the speed of light, at a killing horizon. Okay, and so there could be solutions that don't have this form. We'll see that in a second, but generically, it will certainly happen. So you shouldn't be surprised. There's a sort of simple argument why this happens. If I have a metric and I've got some killing vector field psi and an associated killing horizon, so that psi generates that. And let's assume all the other fields in the theory are invariant under that. So that's the setting. And now let's assume our killing horizon is a bifurcate killing horizon. There's a bifurcation surface on which psi vanishes. And further assume all the fields are smooth in the space-time, at least away from any black hole singularities, but in particular on this horizon and on the bifurcation surface. Now, we're assuming we've got two derivative equations of motion. So there's some effective metric that governs the propagation of a particular degree of freedom. So let's say we focus on some degree of freedom. There'll be some effective metric that governs the two derivative terms in its equations. And those control the sort of propagation, the light cone structure. And it will be built from the metric and other fields in the theory and curvatures and so on. However, the key point is that because all the fields are invariant under this killing vector, so is this metric. So this is a killing vector with respect to this metric. And in particular, the norm of psi is therefore preserved along the flows generated by the vector field psi. Now, on the bifurcation surface of the horizon, you know that this vector psi vanishes. So this norm vanishes, and therefore it vanishes everywhere on the killing horizon. And so what we learn very straightforwardly is that this is a killing horizon not only of our original metric, but also of our propagation metric for this degree of freedom. And that works for any degree of freedom under these conditions. And so we see it's perfectly fine for different propagating modes to have different speeds outside a horizon, yet share the same horizon. It just comes from smoothness, essentially, and a bifurcation surface. Now, of course, it may be that there are black holes in such theories that don't have a bifurcation surface where you have smoothness, and that's fine. I don't think much is known about that sort of question generally in, say, high derivative theories. But a simple and canonical example of a theory where this is certainly the case is Einstein ether. And the point is, in Einstein ether, you have a vector field that's constrained to be time-like with unit norm. And that is simply incompatible with having the field be smooth on the bifurcation surface, where in some sense you have a sort of time reflection symmetry, and this manifestly breaks it. So this field has to vanish there if it's smooth, and it certainly isn't in this case. So typically in Einstein, well, or rather in Einstein ether theory, one would only expect to have a smooth future horizon, but it can't be extended back to a smooth bifurcation surface. That would be the point. And so it's an interesting theory because now it really is the case that one can have multiple horizons for different degrees of freedom. They're not bound to have the same horizon, and in particular, generically, they don't. So what does this theory look like, Einstein ether, in a bit more detail? As I say, many of you are expert on it. I'm going to write it out using Ted's geometric couplings, Ted Jacobson's geometric couplings, because it does look more elegant in that language. We take the ether field, U, we then decompose its gradient, remembering that it's got this time-like norm constraint. We decompose its gradient into an expansion, a shear, and a twist term. And we also have its acceleration. And these expansion, shear, and twist now live orthogonal to the ether itself. And so this is a decomposition of this derivative, but in particular, we can now write the action in terms of these variables, and it takes a very elegant form. It's just Einstein-Hilbert, and we have quadratic terms in these various quantities, the expansion here, the shear, the twist, and the acceleration. And we have a Lagrange multiplier field that enforces the constraint. Now, a sort of obvious point is that if all of these couplings, the couplings of these various terms, C theta, C sigma, and so on, are very small in magnitude, they're dimensionless, so they're numbers. If they're small in magnitude, it's sort of obvious that we're going to recover GR-like behavior in the metric, because the ether will only very weakly back react on the Einstein equation. And so obviously we're going to recover sort of nonlinear GR behavior, and there'll be some ether on top of that. But unless you can observe the ether directly, the Lorentz violating ether, as Astrid was sort of discussing, unless you can observe that directly, you wouldn't be able to see it. And so we're going to be interested in seeing this Lorentz violating ether through gravitational effects. So what we're really going to be interested in is the case that some of these couplings are large, not small. And then there's some chance that nonlinear gravitational physics will have an interesting ether that will back react on the metric and make it look something different to GR. So the theory contains various spin degrees of freedom. The spin 2 graviton has a wave speed governed by the coupling of the shear term. And as we've sort of heard in various talks, the LIGO neutron star merger constrains this very, very tightly to be absolutely a tiny deviation from the speed of light. And so in the rest of this talk, we're going to assume this is exactly 1, and this coupling therefore is exactly 0. So it's got to be 0 to 10 to the minus 15 or so, 1 part in 10 to the 15 or 16. So we'll just take it to be precisely 0. And with that, one still has different other degrees of freedom, spin 0 and spin 1 degree of freedom from the ether, and they have various wave speeds that depend on the couplings. And very interestingly, as shown by Sarbach and one of our organizers, Enrico, this theory is well posed. I mean, it has a good dynamical formulation and can have a hyperbolic formula. So it's a dynamically sensible theory. Now, the observational constraints on this theory changed a fair bit given that LIGO observation, so that they were originally discussed by Jacobson and Foster a long time ago. But more recently, Shinji and collaborators worked out the implications of having this graviton wave speed equal to the speed of light. And one can express some of the constraints in terms of the preferred frame PPN parameters, alpha 1 and alpha 2. They're constrained to be small by solar system observations, and they are related to the various couplings in the theory like this. And so these constrain various couplings to be small. We've already got that C sigma has to be, we're going to take it to be 0. So you might think, well, there's really nothing left except all the couplings being tiny. But it turns out, even there's some extra constraints from various considerations. But even with all of those, there is still some interesting parameter space where some of the couplings are large. And as I emphasized before, that's the regions we're going to be interested in. And I'm going to call them region 1 and 2. These were in this paper here by Shinji and collaborators. So region 1 is going to have one large coupling, and that coupling is going to be the twist coefficient, and that can be order 1. We'll assume it's some reasonable number, not small. And then the other coupling CA has to be 10 to the minus 4 or so of that order in order to satisfy this constraint. And the remaining expansion coupling is then related very closely to the acceleration coupling. So there's one large parameter essentially. And in region 2, you can have two large parameters. The twist and the expansion can now be order 1. Well, by order 1, it's got to be slightly less than 1 if you believe the usual BBN calculations of nucleosynthesis. But let's say order 1, roughly speaking. And then the other parameter, CA, has to be very small. So in fact, smaller than it has to be from this constraint. And if we want to sort of picture those, we can understand I'm suppressing the large twist coupling, and we can sort of draw a picture in the C theta CA plane. Here's region 1, where C theta and CA are related by roughly a factor of 3, and there's a little bit of leeway between exactly where you sit. And the region 2 extends all the way up to order 1 numbers in the C theta axis here, but is tightly constrained to it. And there's a sort of transition region where these couplings are both very small of order 10 to the minus 7, which we're going to exclude because that's a slightly more subtle region, but it's also very small, so we're just not going to consider it. But the key point here is that there's a couple of large parameters, or 1 or 2 large parameters. And so surely you might think black holes are going to differ from Kerr because the ether is going to be non-trivial, it's going to backreact on the metric, and it will no longer look like Kerr. Now, static black holes were found some time ago. So Elling and Jacobson started this and developed the methods to think about it. And there was nice work with Enrico and Thomas Sotiriou and Ted more recently, but still a long time ago, looking at these black holes. This was, of course, before these new phenomenological bands from LIGO. Static black holes are relatively straightforward to construct. They just involve solving ordinary differential equations. And in fact, recently, they were constructed in what I would call region 1, where only the twist term is large, where the other parameters were small. And it was actually found that the solutions look a lot like Schwarzschild, and they're very close to Schwarzschild. However, in a sense, it's obvious that that's going to happen because in the spherically symmetric case, the twist for static spherical symmetry, the twist of the ether automatically vanishes. It must vanish. And so the only large term you have in the Lagrangian comes from the twist, but the twist is exactly 0 for symmetry reasons, then and the remaining couplings are small, it's sort of obvious you're going to get GR-like behavior. And you find Schwarzschild. However, I emphasize when you've got a rotating black hole, it's now not the case that the twist will vanish identically. There's no symmetry that will make it vanish. You would expect it to be non-zero. And so it's, again, we would expect some deviations from Kerr, potentially order 1 deviations. Now, let me talk a little bit about how we might construct these black holes. So, as I said, in the case of static spherically symmetric black holes, it's what I say very simple to do. It's very clear how to proceed. You have ordinary differential equations that can be solved as the so-called shooting problem by imposing, what you want to do is impose boundary conditions of asymptotic flatness, for example, and then regularity at horizons. And you need both of those things to get a regular, to make the Einstein equations sort of well posed, to have distinct solutions. And so you basically, you start out at infinity and you aim you shoot your functions in, and you tune your data in order to get regular horizons. So in practice, it's a bit tricky to do, but in principle, it's simple to set up. Now, the stationary solutions are a different story. They're much more complicated because now one's forced to work with PDEs. There's a very old method for solving, for looking at black holes or stationary solutions in GR that's based on a perpetual-like ansatz. And that actually goes back a long time, decades, to work on neutron stars. For example, in this paper, this is a nice paper looking at black holes in Einstein-Dilaton-Gauss-Bonnet theory, so a high derivative theory. Again, it's a theory that potentially has different wave mode horizons, or could have different wave mode horizons with its high derivatives, but nonetheless, there is a common killing horizon. And so one has a metric of this form here. One writes a metric of this form. One chooses a specific coordinate system to write the metric in, and it's important for these methods that you do that. And then you have some functions A, B, C, W here, which one solves for. And these come from solving the Einstein equations or some subset of the Einstein equations, and they essentially obey elliptic differential equations. So something like Poisson, but nonlinear versions with sources. It's complicated, but you can solve them as a boundary value problem on a 2-dimensional domain made by the radial coordinate and the angular coordinate on the sphere. And one has to impose some sort of boundary conditions at the boundaries of this domain. And those are regularity of the horizon and the asymptotic flatness that you want. And in particular, I should have also written here, one also fixes at the horizon the surface gravity and angular velocity of the horizon when one writes down the data. So it's rather nice. You get to fix what you want to fix, and then you solve this PDE system numerically, which can be non-trivial to do in practice, but in principle, it's okay. Now, going beyond 4D stationary and asymptotically sort of flat, it's a bit less clear how to proceed if you want stationary solutions. So if you're in a more exotic settings, like high dimensions, for example, that old method doesn't work. And myself and others introduced some more general methods to deal with stationary black holes, where you don't solve the Einstein equation, which would be this term and this term. And of course, you're solving matter as well, if there's matter. But you add to the Einstein equation what I would call, a new term to make it what I would call the harmonic Einstein equation. And this is the gradient of a vector. And that vector is constructed from the metric and its connection through a sort of trace of the connection, together with another connection I would call the reference connection. And that is constructed itself from a reference metric. So you have not only the metric, but you have a fixed smooth reference metric. And that reference metric really plays the role of fixing the coordinates in your problem, because you can't numerically deal with the Einstein equations unless you deal with the diffeomorphism invariance. You have to fix the coordinates that the solution will be presented in. Otherwise, you'd have a horrific infinite degeneracy of solutions, and no numerical method will find a solution. So you solve this modified system, and one of the key points is that it's high solutions. You might think, well, I don't want solutions of this. I want solutions without this term here. But it turns out that actually solutions with a non-zero vector psi are highly constrained and often just can't exist. So for example, in the vacuum or anti-de Sitter case, in any number of dimensions, Pau Figueres and I, and also in earlier work with James Lucchetti, showed that the only solutions to this equation are ones where psi vanishes. You can also see quite straightforwardly, just by sort of doing, for example, a Wick rotation to Euclidean time, that this system, well, firstly, the principal symbol of it looks elliptic. And secondly, by going to, for example, Euclidean time, you can see that this gives you a well-posed elliptic system of PDEs, which you can then solve. On the other hand, in the stationary case, it's a little bit less obvious, but again, you can do a little bit of work and see that, again, it does give you an elliptic formulation in the exterior of the horizon. And so what one does, one has a stationary black hole. Well, I've sort of drawn a static black hole, I suppose, here, but the details inside the horizon are irrelevant here. What we're really interested in is the interior, the exterior, sorry. And what one does is one solves this PDE problem on a domain which extends a constant time slice from space like infinity to the bifurcation surface of the Killing horizon. And again, you impose asymptotic flatness as a boundary condition here, and the boundary here, you impose regularity of the horizon, surface gravity, and any angular velocities. And so this is, you know, that's then it's a very good method for finding black holes, but it's clearly not going to work if you don't have a smooth bifurcation surface. And so it's not going to work for Einstein ether. And so the new technique we use is instead to use the same harmonic formulation, the Einstein equation, but now with an ingoing chart that pierces through the metric horizon, and in fact, any other horizons that other wave modes might have. And this doesn't require any smoothness. It just requires smoothness of the future horizon, not the bifurcation surface. And it's got some quirks. Smoothness of the metric components implies smoothness of the horizon. So you've got to work in the space numerically of smooth functions that parameterize your metric to ensure this. And the problem, once you get inside all the horizons, is certainly not elliptic anymore. And so there's no inner boundary condition here. That's the interesting thing. The regularity of the horizon and boundary conditions out in infinity should be sufficient to determine the solution everywhere, including in the interior here, which is interesting. So there's nothing to do at this innermost point. It's sort of determined by what's happened outside. There's some extra subtleties, like you don't get to fix the surface gravity and angular velocity like you do in the other method, but that's fine. There are ways of dealing with that. You just have to constrain that data. And the method, I would say, works reasonably well in the sense it's not nearly as robust. It requires a bit more shepherding to get solutions, but one can do it. For Einstein ether, you've got to deal with 10 metric functions. You've got all the functions in the metric that you've got to include. They only depend on 2 coordinates, but there's a lot of them. All of the components of the ether for and the Lagrange multiplier field. And you spend a lot of time looking at plots like this, which are some of the functions that parameterize the metric or ether and so on. Now, let me tell you about some of the results. Well, the first thing one could do is one can go to the old black holes that were found. So, for example, the ones in the paper by Enrico, Thomas Sotiriou, and Ted. And so, for example, in that paper, for a range of this over a range of values here from sort of 0 to 1, black holes were found, static black holes were found, and you know, you can look at their properties. So for example, you can look at the equatorial radius of the horizon. Well, the value for GR given the mass and spin of the black hole divided by the value that you find for these ether black holes. And for this sort of value of coupling, there's something like a 7% variation from GR in the static case. That's what they found. And you can now add spin to that and see how it changes. In fact, it really doesn't change very much, that particular quantity. You can look at the ISCO frequency, for example, and compare it to GR, and you find some sort of variation. But these are not phenomenologically viable black holes. And so the question is, what happens when we look at black holes that are phenomenologically viable? Okay, what do we find there? So what we're going to do is construct, for fixed spin, families of black hole solutions where we tune a parameter so that we start outside of the phenomenological regions, and then that parameter, as we tune it to 0, is going to take us into the phenomenological region. Because in the phenomenological region, you've got some very small couplings, they can be problematic numerically, but what you really want to understand is what's the limiting behavior as the couplings become small, and that's enough to tell you what's going on. And so, for example, we've taken a bunch of families, which I've called 1A, 1B, 1C, 2A, 2B, 2C, and so on. And this, you don't have to remember this, but basically we take the acceleration parameter CA to be the coupling that we're going to tune. So we'll start with it large, we'll find some black holes, and then we'll take this to be smaller and smaller. And in these families, if this got to 10 to the minus 4 or less, we would be in the phenomenological region. In these, if it got to 10 to the minus 7 or less, we would be in the region 2 phenomenological region. Okay, but when epsilon is non-zero, you know, is order 1, then we're certainly not. So we're interested in the limit for these various families as we take epsilon to 0. And these families, they go into these phenomenological regions 1 and 2, but they go in different places. So for example, in this plot I had before, if I'm looking at this family, you know, this family for large epsilon is somewhere way out here, and then as we tune epsilon down, it comes into region 1, but with a particular value of C omega that's a half, and these other families would have a different value, and so on. So what happens? So we find these black hole solutions, and we tune epsilon to be smaller and smaller, and actually what we find in all the cases we look at is that we recover Kerr. So we're fixing the spin. This is the angular momentum over the mass. In this case, it's 0.7. So it's not super fast spinning, but it's reasonably spinning. And these are all the different families. And this is epsilon, which is the acceleration parameter. Remember, that's the thing we've got to take small to get into the phenomenological region. And this is a log-log plot where I'm plotting on the y-axis the L2 norm of one of the functions that parameterize the metric. And the point is that when this function is 0, the metric is precisely, sorry, when all the functions as we choose to parameterize things are 0, then the metric is exactly Kerr. So we sort of deform. It's useful to build the metric by deforming away from Kerr with our unknown functions. But in particular, one of the nice things is then by taking the L2 norm of this over our domain, if this goes to 0 and all the other metric functions go to 0, we know we've recovered Kerr. And here we see that indeed that's happening. This slope on the log-log plot corresponds to a linear decay of this quantity with epsilon. So as we go into the phenomenological region, we're recovering Kerr with this spin. Okay. And all the other metric functions obviously behave the same way. Now, here's an interesting quantity. This is the L2 norm of the twist. So what's happening to that? Well, you can see exactly the same behavior for all of these different families. This twist is, you know, if you extend, I mean, we haven't extended to, I mean, these are sort of order 1 epsilons. You could extend to even larger epsilons if you wanted. But you start with some reasonable numbers for the twist, and they all drop down linearly to 0. And so the twist is vanishing for these solutions as you go into these phenomenological regimes. Okay. Now, that makes some sense. In region 1, the only large term in the action, the only large coupling, I should say, in the action is the twist coupling. So if you're going to recover Kerr, it had better be because that large twist coupling is multiplying a small twist. And so this is the mechanism for the region 1 parameter space whereby you can recover 4D behavior. The twist is vanishing there for these solutions. What about the region 2 ones? There you have a large twist coupling, but also a large expansion coupling. So if you're recovering Kerr, the expansion must be going to 0 for the region 2 solutions. And indeed, that's exactly what you find. So this is the L2 norm of the expansion. It's going to 0 precisely for the region 2 families. Whereas if the region 1s, where that expansion term is multiplied by some small coupling, it doesn't have to be small, so it will naturally have a small back reaction because of the small coupling, and it doesn't go to 0. But interestingly, it does go to a universal form. So actually, one finds, one finds that if you look at the ether itself, not just its some sort of cruder quantity like the L2 norm of the expansion, if you look at the ether for all of these different families, in this limit epsilon goes to 0, the ether is the same form. All the metric the components for it are the same in the limit epsilon goes to 0 for the region 2 family, and they're all the same for the region 1 family, although different to the region 2 family. So not only are you recovering Kerr, but you're recovering a universal ether behavior that doesn't care about where you are in these phenomenological regions. So why is this all happening? Now let me try and explain what's going on as we understand it. Here's our action. Perhaps it's obvious to you by now from what I've said. Here's our action. We have no shear term. We've got our we've got our large twist coupling. And in region 2, we also have a large expansion coupling. And this CA is small. This coupling here is small. So what we're seeing is that in region 1, the twist dynamically chooses to be small as we go into that region. And in region 2, both the twist and expansion dynamically go to be small. And that's why we get a small back reaction on the metric, and then we can recover Kerr behavior. So we can think about this more formally. Let's do this for region 2 as an expansion in CA. So let's call CA epsilon as we were. Region 2, we've got these two big couplings. So what we're going to do is we're going to think about a solution as a perturbation in epsilon about some leading order solution, which is like the epsilon 0 limit. And how do we choose that? So what we're going to choose is that G bar, and there would also be potentially matter fields, not if you're in vacuum, G bar and the leading order behavior of the matter fields would just be that of a standard GR solution. Okay. The ether here, we are then going to choose to be twist free because we know in the epsilon goes to 0 limit, we've seen it should be twist free from the black holes. A twist free ether can always be written in this form in terms of what I would call a twist potential F, which is a scalar function. And then another scalar K, although that is determined in terms of F just from the norm condition. So really there's just one scalar function once you have your ether be twist free. And of course, now our leading action has not only a twist term in, which identically is going to vanish at leading order because of this twist free behavior, but it's also got an expansion term. What about the expansion? That's not generally going to vanish. And the expansion is given in terms of this twist potential like this, in terms of this leading data, so at leading order. And for consistency, when you think about the back reaction of that expansion term, this must also vanish. And so what we're going to do is we're going to take this vanishing as an equation of motion, essentially for F, for our leading solution. And this takes the form of an elliptic equation, an elliptic PDE second order on the slices of constant F. So on the foliation defined by this twist-free ether. So it's a slightly complicated condition, but nonetheless, this leading solution we have, it's just 4D-GR with a twist-free ether that's also expansion-free painted on top. And then at least locally, everything's got a good equation of motion, everything's determined. And then at order epsilon, there'll be corrections to that. So the solution, won't be exactly that, but if epsilon is small in region 2, it's 10 to the -7 or less, there'll be very, very small corrections. And it's worth emphasizing the ether conditions, twist-free, expansion-free, don't depend on the actual values of the couplings or indeed C epsilon. So there's just a universal equation of motion for the ether in this limit. So we don't have a proof that all solutions have to take this form. That would be very, it'd be remarkable if one could prove that, and very interesting. But certainly that's what we see in our numerics. We only see black holes that go in region 2 as we approach region 2 that take this form. We haven't found any other non-Kerr-like behavior. Maybe it exists. And I would also say that whilst this is potentially a consistent solution, and there's equations for this twist potential, this is just a 4D solution, and in principle, one can perturb around it, we don't have a proof that solutions to all those equations exist. So, are you guaranteed a solution for this twist potential exists? And for example, if one was in cosmological boundary conditions where far away the expansion doesn't vanish, out at spatial infinity, then it's obvious you can't satisfy this.
Toby,
but for asymptotic flatness, oh yes.
Sorry, you have around 5 minutes left.
Yes, I'm nearly done. Thank you. Thank you. So, but with asymptotic flatness, it seems reasonable that you probably can always solve these equations, or at least in some reasonable set of for initial data. Now, region 1 is a little bit more complicated. One can proceed in exactly the same way. You take a 4D-GR solution, a twist-free ether, and expand about it. But it's slightly confusing because you might think nothing determines F. Remember, there's no large expansion term. So at leading order, this is all you need for consistency. And F looks like it's completely free, which sounds a bit fishy. But it turns out, actually, when you look at the equations at order epsilon, there is a consistency condition that arises that only depends on this leading data. Looks a bit more complicated. Don't worry about the form too much, but it basically takes the form of a 4-derivative equation on F. Now, again, that's even more complicated. We've no idea generally if you should expect solutions to exist given various asymptotic conditions, but certainly that's what's happening in the stationary black holes we're looking at. So anyway, in summary, there are these numerical methods to study black holes in theories where you have multiple horizons for the different wave mode speeds, which is obviously Einstein ether is the canonical example of that, but there are other examples of theories. We've applied it to Einstein ether. But interestingly, in the viable theory, where you impose the various constraints, in particular the strong one from LIGO, one finds that the solutions, the black hole solutions, the only ones we found, look like that of GR, they're Kerr, with a sort of universal ether painted on top of it. And the ether only, the form of the ether really only depends on the parameters of the Kerr solution, the angular momentum and mass. It doesn't really care about precisely where you are in these phenomenological regions, the couplings. And, we would argue from what I've just said that this is a more general phenomenon. There probably exist many classes of solutions, dynamical metrics, not just stationary black holes, dynamics with matter and so on, where basically in this region 1 and region 2, even though some of the couplings are large, the theory in the end just looks like pure GR behavior coupled to normal matter in the usual way, then with this sort of twist-free painted on ether going along for the ride, but having negligible back reaction, not changing things, which depending on your point of view could be good or bad. Anyway, so that brings me to the end, so thank you.
Okay, thank you very much, Toby. Now we have time for questions. If anybody want to ask something, just please raise the hand. Okay, there are a couple of questions. First by Katy.
Hi, Toby. So when you're talking about tuning the epsilon, is that because you basically started with a large epsilon and found your solution, and then you use that as an initial guess for the smaller epsilon? Right, I see.
Exactly. Yeah. So you have elliptic equations, so you solve them by something like a Newton method. You start with an initial guess and refine it. Yeah. And it's rather natural then. Once you found a solution, it's easy to move around in parameter space, but you could find solutions straight off. It actually seems to be, as I said, there's a certain amount of shepherding. So once you've got a solution, it's a bit like gold dust, and then you can move around in parameter space. It's quite difficult to jump to the small epsilon solutions directly. Yeah. Maybe it could be done, but yeah.
But if I understood what you're saying, you're not sure that there's a unique solution to the, so if you find one, you can't guarantee that that's the unique solution that you found.
Oh, I see. Yes. No, I mean, that's standard with any elliptic equations. And that, I mean, unless there's some analytic proof, you know, it's all, when you use Newton method, it's like finding roots in an equation. You might find a root, but you've no idea if that's the only root. So it's all about basins of attraction. And, you know, we haven't found anything that doesn't look Kerr-like in these limits, but it could just be that we have to start in some, you know, quite far off place to begin with to find such a thing. So it could easily not be found.
Okay, thanks.
Thanks.
Okay, next one in the list is Enrico.
Yeah, I couldn't picture what the ether really does. So that small f, so the ether is orthogonal to surfaces of f equals constant. What do those surfaces do in the limit epsilon goes to 0? And I'm asking this question because I was thinking of the universal horizon. Is there a universal horizon in the limit epsilon going to 0?
Yes, I think there's a universal horizon for all of these solutions.
Okay.
Yeah. In fact, so in these phenomenological limits, the spin 0 and I think the spin 0, I forget, let me go back to my slide. You know this far better than I do, I'm afraid. Yes, so in these limits, the spin 1 speed is always becoming very large.
Okay, so
but the spin 0 speed may also generically becomes large, but in region 2, if c theta is small, it can be finite. So one of the wave speeds is always very large, and so basically the horizon for the spin 1 degree of freedom sits very close in the limits of the universal horizon. They're basically the same thing, and that all has to be captured. You have to capture all of these horizons in your domain so that the smoothness is correctly imposed, so that you have a good solution.
It makes sense now. Thanks.
Okay, so we'll have another 2 questions as it's the last talk. I think it's okay to spend some time on them. Nicola?
Yes. Hi, Toby. Thanks for a very nice talk. It was pretty interesting. So I would like to ask whether you checked if the solutions you found are also solutions in Ojava gravity. I'm asking this because, like, I would expect that these twist-free solutions, they have the exact same form for the other field that you would find in Ojava. And if you did this, did you do any mapping between the parameters that you're using?
Yeah, so that's a good question, and I really should have an answer for it, but we haven't looked at it. But I suspect I should know the answer. I mean, I have no idea. I'm afraid so Ted might be able to, if Ted's online, he might be able to say something wise about this. But I'm afraid I'm not familiar enough with Ojava gravity and all its variants to know whether these solutions directly transfer. But I suspect one could think about using similar methods to find black holes in those settings.
No, I'm saying this because this reminds me that like in Ojava, there are these solutions, like static solutions, which are Schwarzschild plus an unfolding ether field. So here it looks exactly the same, like you have a Kerr solution or Kerr very similar to Kerr plus some ether that doesn't back react on the metric.
Yeah, that's right. It's probably the same. Like, it may be a similar mechanism. I'm not sure how these phenomenological limits tie in with Ojava, though. Sorry. Yeah, but of course, the one thing I would say, in the spherically symmetric case, it's all a bit simpler because the ether is automatically twist free. So what's less obvious is in the rotating case how it might work. But yeah.
Okay, and the last question is by Thomas.
Hi, Toby. I thought I had understood, and then Enrico asked his question, and I realized that maybe I didn't. I wanted to ask the same question. So the ether is not hypersurface orthogonal throughout the space-time in your solution, is it? In the fully numerical solutions?
Yeah. So the ether in general is absolutely not hypersurface orthogonal. So it's not twist-free. It generally has a twist.
Yeah, exactly.
However, in the limit, when I take these one parameter families, which in this limit epsilon goes to 0, sort of go into the phenomenological regions, in the strict limit epsilon goes to 0, it becomes twist-free.
Okay, but right, but I mean the numerical the full numerical solution that you find in this parameter doesn't correspond to the limit epsilon equals 0, right? I mean,
no. No, absolutely.
So then what I wanted to ask is that in the general solution, have you checked if the ether becomes orthogonal to some hypersurface in the space-time? You know, generally it's not hypersurface orthogonal everywhere, but you know, is there some one surface basically on which the ether is orthogonal, which could be a universal horizon, even if you know, could potentially act as a universal horizon, even if the ether is not hypersurface orthogonal everywhere?
Sorry, isn't the condition that the twist vanishes? So maybe you're asking, does the twist vanish locally somewhere?
Yeah, exactly. Does it vanish locally, just on one surface?
Okay. Yeah. So I think I'm trying to remember the various plots. We haven't really looked in detail at this, but from my memory, the twist. I don't think it vanishes anywhere. I don't think it vanishes except out at infinity.
Well,
so I think it's
0, right?
I think the norm of it is positive everywhere. So I think that's the case. Possibly except the pole, you know, the pole of the black hole. Yeah. So it may. Yeah. Honestly, I'm not sure. But so I don't think there's a sort of like a surface sitting at some approximate radius that's hypersurface orthogonal. There might be a sort of trivial surface which you're less interested in, like the equatorial plane, which is orthogonal to the
Sorry,
ether.
Could it be because they are not? Maybe I understood wrong, but are you integrating from r equals 0 or from some killing horizon? Because maybe the universal horizon might be inside this region, so like between 0 and the radius where you start integrating. So maybe you don't.
So the way.
No.
The way we solve this is as a boundary value problem. It's an elliptic system, and when you work with PDEs, you can't use a shooting method. So you can't sort of start at infinity and shoot into the horizon or vice versa. It just doesn't work. So what you have to do is you have to solve everything all at once with boundary conditions in the two places. And as I described in this ether setting, it's even slightly more complicated because the boundary conditions at the horizon really is just their smoothness. And so actually you have to take a slice that goes through the horizons, just work with the space of smooth functions and require asymptotic flatness. And so you just solve it all at once. And as I was saying to Enrico, I think we extend far enough inside the horizons, that we capture the universal horizon as well. They're all smooth.
Yeah, well, it seems to me you do have a universal horizon for epsilon equals 0, certainly, and that's the parameter space. It's not obvious to me for epsilon different than 0, because you showed the L2 norm, but
no. Yes, sorry. I mean, we've I haven't got the data to show you in the keynote, but we have found the universal horizon and it's there and smooth in all of the solutions. Yeah, exactly. Yeah, away from this limit. So what I was saying earlier is in the limit, it's sort of obvious if, given that we've captured the spin 1 horizon, we basically captured the universal horizon, but away from that, we also captured the universal horizon. I don't think we need to, But it turns out in our computational domain, the horizons all sit relatively close to each other. That's not to say that they're the same size, it's just the way our coordinates work. So we'll end up capturing them all, including the universal horizon, I think.
Can I ask one more question that doesn't have to do with the universal horizon? I mean, actually does have to do with Einstein ether theory. It has to do with your numerical method. So I mean, okay. So now that you're looking at, basically you're looking along a null slice, right? You're solving the problem, and so past. You said that past the horizon, the problem becomes hyperbolic, which I take it to be just because the killing vector becomes space-like inside, right? The one that was time-like outside.
Yes, exactly.
Right? And so how, I haven't actually quite understood how you determine then how you solve the hyperbolic problem in the interior.
Yeah, okay. So I suppress many of these details because generally people don't want to hear them, but I'm delighted if you do. So apologies to everyone else. So as I said, so our computational domain, which, but at the end of the day, we write the metric in some ansatz, and we actually use something like a Kerr metric, and then we deform all those metric components by the various 10 functions, which are now functions of our non-trivial coordinates, r and theta. And we take Kerr in ingoing Eddington-Finkelstein-like coordinates. So if it was exactly Kerr, this would be a null slice going in through the Kerr horizon. And we don't want to extend right up to the singularity, because obviously that's going to cause us problems. We won't be able to solve smooth functions there. We won't get smooth behavior, but we just extend inside far enough. Now, a priori, and here's a tricky point, when you start solving your equations, you don't know where the horizon is. It's something you read off a posteriori once you've got your solution. So what you work with is the space of smooth functions to try and ensure that, whatever, if you've captured the horizons, they're going to be smooth, and you hope that your coordinate chart extends far enough in that you correctly impose the boundary condition that all the horizons that you have are smooth. How do you work with the space of smooth functions? That's a question. So as I was saying to Katy, when you solve these elliptic PDEs, you use something like a Newton method. You start with a guess, and then you update it. And you repeatedly do that until you converge to the, to whatever accuracy you want. And one of the key points about that is if you start with a smooth initial metric, the update should be smooth if it's going to converge to something. So if it's going to converge to something sensible, each time you update the metric, the various metric functions just get updated by some smooth way. And so it preserves smoothness. And that's, in some sense, how you impose the boundary condition that all the horizons that you get are going to be smooth. Now, of course, there's no guarantee that this Newton steps, just like with Newton-Raphson, as we all know, there's no guarantee it's going to converge. And if it doesn't converge, it quickly degenerates to nonsense. And anyone who's done this has spent a lot of time looking at nonsense. But when it does converge, and you can go and check and look at the solutions, but when it does converge, you do get smooth metrics. And in fact, with this method, there's this extra vector field that you can sort of a posteriori read off, and it should be 0 if you found a solution to the Einstein equations. And actually, it's a good check of whether you've converged correctly and numerically to the, whether your approximation is a good numerical approximation to a real solution to the Einstein equation, whether that is properly converging as you increase resolution to 0. And indeed, it does in all the solutions we've constructed. Yeah. So I hope that answered your question.
Yeah, that's fine. Thanks.
Okay, so let me finish by thanking you again, Toby, for your talk. And also, I want to thank all the speakers of today and also Thomas for leading the discussion. And just before finishing, 2 quick comments. One, remember that we have a Slack server where you can add questions that you couldn't make during the talks or after the talks. Please, the speakers, if you can check the Slack also to reply, that would be very nice. And I think there is a question right now for Lasma actually. And well, we'll see you. We'll see all of you again on Monday. We start at 3 Italian time. 3 p.m. Italian time on Monday again. Well, thank you very much for being here. I don't know if Enrico wants to say anything before closing the first week.
Not really. Well, thank you, everyone. And I hope to see you on Monday again. And thanks to all the speakers, today's speakers and yesterday and the day before. See you on Monday. Enjoy your weekend. Bye-bye.